पहला जो हमारा प्रारंभ होगा वो 1 से by standing Adiyoshi Ratibulwari Dr. Amashinga इस प्रतिदान नवोदयोत्साह में और आज के इस कॉन्फ्रेंस के उद्घाटन के मैडम उपस्थित हो रही हैं अवसर निवेदन है कि उनका और चार भी चमकेंगे तो क्या बात बनेगी। 100 साल भी चमकेंगे तो क्या बात बनेगी। आप आ गए तो आज की औकात। शुक्रिया आपका आने से रौनक तो बढ़ी। शुक्रिया आपके आने से रौनक तो बढ़ी। वरना ये महफिल जज्बात अब बुरी नहीं। मंच पर आशीन वीरमंडल विश्वविद्यालय के प्रभारी सांसद डॉक्टर आमोश I invite all the dignitaries to come on the dais and take their responsibilities so that this program could be starting in time, new time, by concluding all the preliminary activities like the lighting of the lamp and welcome song. So all the dignitaries are requested or is requested to come on the dais. सभी लोगों से अध्ययन है हमारे देश में सभी लोगों से आगे रहते हैं कि स्थान पर बैठने के लिए Dr. Shiva Chaudhary, you are requested to come on the dais. मैं देख रहा हूँ कि मीडिया में भी जो सबसे हो चुके हैं, मैं उनका भी हार्दिक अभिनंदन करता हूँ और अब स्वागत किया गया हमारे प्रभारी सांसद डॉक्टर आमोश जी का उद्देश्य और आज से स्वागत किया जा रहा है। आगे मंच पर विराजित हैं डॉक्टर एकदल सुंदरी, जिनका आप पूर्ण भारत से स्वागत हो रहे हैं। डॉक्टर एकदल सुंदरी इनके स्वागत मैं आग्रह करूंगा हमारे जो कन्वीनर हैं डॉक्टर संदीप कुमार साहब, वो आगे आए और डॉक्टर चतुर्वेदी जी का पूर्ण भारत से स्वागत करें। एमएलटी कॉलेज सहरसा के प्रधानाचार्य डॉक्टर BN जी का पूर्ण भारत से स्वागत करेंगे। डॉक्टर मयंक भागवत मंच पर उपस्थित होने के लिए मैं डॉक्टर आरके सिंह से आग्रह करूंगा कि वो मंच पर उपस्थित होने की कृपा करें। मैं आग्रह करता हूँ डॉक्टर विपिन कुमार सिंह को कि वो आकर डॉक्टर आरके सिंह को पूर्ण भारत और बुके देकर सम्मानित करें।
सम्मानित स्पीकर सुनो ना
और मैं आग्रह करूंगा डॉक्टर सुमन स्वराज से मैं आग्रह करूंगा डॉक्टर सुनील जौहरी जी से कि वो इस मंच पर आए और डिग्री कॉलेज मधेपुरा के प्रधानाचार्य डॉक्टर के यादव जी का पूर्ण भारत से स्वागत है। अब मैं आग्रह करता हूँ डॉक्टर अजय कुमार दास जी से कि वो आर कॉलेज सहरसा के डॉक्टर अरुण कुमार जी का बोलना स्वागत करें। डॉक्टर एस एस साहब इस सभा में उपस्थित हैं तो कृपया यहाँ आने का प्रश्न करें। डॉक्टर एस एस साहब जिसे मैं आग्रह करूंगा कि वो एस कॉलेज सहरसा की प्रधानाचार्य डॉक्टर अशोक सिंह को पूर्ण भाव से स्वागत करें। डॉक्टर एस एस कॉलेज सहरसा के प्रधानाचार्य डॉक्टर अशोक सिंह जी का स्वागत करते हैं। डॉक्टर अशोक कुमार साहब बॉटनी, डॉक्टर अशोक कुमार साहब बॉटनी से मैं आग्रह करूंगा कि वो नरेंद्र जी का फूलवार से स्वागत करें। डॉक्टर अशोक कुमार नरेंद्र जी का स्वागत करते हुए डॉक्टर अशोक कुमार। BNMU से आग्रह करता हूँ डॉक्टर अशोक कुमार साहब बॉटनी डिपार्टमेंट प्रोफेसर BNMU का स्वागत करें। डॉक्टर अशोक कुमार साहब डॉक्टर टीवी त्रिपाठी जी से मैं आग्रह करता हूँ कि वो मंच को संबोधित करें। डॉक्टर टीवी त्रिपाठी। मैं डॉक्टर प्रदीप जी से आग्रह करूंगा कि वो डॉक्टर त्रिपाठी जी का फूलमाला से स्वागत करें। त्रिपाठी जी का स्वागत करते हुए डॉक्टर पीसी। अब कार्यक्रम के भाव को आगे बढ़ाते हुए एक दीप प्रज्वलन का कार्यक्रम है। सभी संबंधित व्यक्ति दीप प्रज्वलन के लिए तैयार हैं। हमारे किसी भी कार्यक्रम को प्रारंभ करने के लिए यह एक शुभ चीज माना जाता है और हम यह भी मानते हैं कि इस काइंड ऑफ विक्ट्री और अंधकार पर प्रकाश का विजय आज के इस दीप प्रज्वलन का भी उद्देश्य यही दीप प्रज्वलित करते हुए हमारे बीएनएमयू विश्वविद्यालय के वाइस चांसलर मैडम डॉक्टर आरके सिंह, डॉक्टर डॉक्टर आरती जी और डॉक्टर चंदू प्रज्वलित करते हुए आज के इस सेमिनार और इसी कड़ी में मैं एक दो पंक्तियां छोड़ता हूँ कि शौचालय में भी आ जाए तो बैठे हुए वो बात बता रहे कि सिर्फ आपके आगे से ही बैठे कराना पड़ेगा, आपके आगे से ही बैठे कराना पड़ेगा। के बाद अब हम आगे बढ़ते हैं कि किसी भी कार्यक्रम की शुरुआत हमारे इस मिथिलांचल की परंपरा में और अन्य जगहों में भी देखा जा रहा है और वो भगवती वंदना से और मिथिलांचल में भागवती विद्यापति द्वारा रचित भगवती वंदना जय जय भगवती बहुत ही प्रसिद्ध है, जन जन के कंठ में विराजमान है। तो मैं विश्व प्रकाश की एवं उनके सहयोगी से आग्रह करता हूँ कि वो जय जय भगवती से अपने इस कार्यक्रम की शुरुआत विश्व प्रकाश जय जय भगवती प्रस्तुत करते हैं। इस कैसे भैरवी गायन के विभिन्न प्रकार से विनाश समय हमारे अब मैं आग्रह करता हूँ रूपम से कि वो मंच पर आए और हमारे अतिथियों के स्वागत में एक स्वागत गान प्रस्तुत करें। रूपम से आप सबको बता दूं कि हमारे विश्वविद्यालय के साइंस हुआ मंच पर राजीव बोल चुके हैं और फिल्म से ही उनका फूल माला से हम लोग स्वागत करें और ये स्वागत हम लोग और मैं आग्रह करूंगा अपने कन्वेंशन से कि तीन साल का स्वागत वो अपने कर्मयों से पूर्णमाला के साथ करें। एक साल का स्वागत करते हुए डॉक्टर नवीन कुमार जी का स्वागत करते हुए हमारे कन्वेंशन का संदीप कुमार और बिना किसी विलंब के अब प्रस्तुत कर रहे हैं रूपम सिन्हा जी अतिथियों के स्वागत में एक स्वागत। हेलो हेलो धन्यवाद। थोड़ा सा हल्का फुल्का हुए इस तो गीतों के पश्चात और ये आवश्यक भी था। मैं पंक्ति कहना चाहता हूँ कि चेहरे पर हंसी और दिल में खुशी होती है, चेहरे पर हंसी और दिल में खुशी होती है, सही मायने में यही जिंदगी होती है, सही मायने में यही जिंदगी होती है। और हंसना किसी इबादत से कम नहीं, और हंसना किसी इबादत से कम नहीं, किसी और को हंसा दो तो बंदगी। मैं आग्रह करता हूँ डॉक्टर दीपक कुमार जी से कि वो हमारे जरूरी के हेड आए हुए हैं, उनके सम्मान में फूलमाला और बुके देकर उन्हें सम्मानित करें। डॉक्टर दीपक कुमार, डॉक्टर अरुण कुमार जी को सम्मानित करेंगे फूलमाला और पान से।
आप कीजिए। हाँ इसलिए
और मैं पुनः डॉक्टर कमलानंद झा जी से आग्रह करूंगा, मैं डॉक्टर कमलानंद झा से आग्रह करूंगा कि हमारे विश्वविद्यालय के बॉडी के हेड प्रोफेसर रमेश कुमार जी आए हुए हैं, उनका वो फूलमाला से स्वागत करें। डॉक्टर कमलानंद झा, डॉक्टर रमेश कुमार का स्वागत करते हैं।
कार्ड का कार्ड खोल दो।
और कार्यक्रम को हम आगे बढ़ाते हैं। अब हमारे कार्यक्रम का जो अगला पड़ाव है, पुनः एक और निवेदन आया हुआ है कि हमारे कृषि विभाग के विभागाध्यक्ष हैं डॉक्टर सीपी सिंह साहब, मैं अजय जी से आग्रह करूंगा कि वो उनको फूलमाला से सम्मानित करें। डॉक्टर विजय कुमार जी व्यस्त हैं, डॉक्टर विजय कुमार जी उनका फूलमाला से स्वागत करें। डॉक्टर सीपी सिंह का स्वागत करते हुए डॉक्टर विजय कुमार। फूल माला और आग से स्वागत और चादर से स्वागत करते हुए डॉक्टर सीपी सिंह साहब का डॉक्टर विजय कुमार के द्वारा अब यह दौर समाप्त होता है और हम आगे की तरफ बढ़ते हैं। हमारा अगला पड़ाव है वेलकम एड्रेस बाय डॉक्टर डीएन झा, प्रिंसिपल एमएनटी कॉलेज सहरसा। ये आपने अभी तक बहुत ही पहले का परिचय दिया है, थोड़ी विलंब होती है, होना भी स्वाभाविक है। इस पॉलिटिकल साइंस के हमारे हेड भी यहाँ उपस्थित हैं डॉक्टर रंजीत कुमार, उनके स्वागत में मैं सौद साहब को आग्रह करता हूँ, डॉक्टर सौद साहब को कि वो डॉक्टर रंजीत कुमार जी का फूलमाला से स्वागत करें। डॉक्टर सौद साहब, डॉक्टर सौद साहब हमारे इतिहास राजनीति विज्ञान विभाग के हेड का बोलबाला से स्वागत डॉक्टर और फूल से स्वागत।
इसके बाद जो है प्रेस 2 मिनट का फाइट लेगा मैडम, 2 मिनट का प्रेस फाइट लेगा 2 मिनट।
अब कुछ प्रेस वालों को भी आवश्यकता है कि वो हमारे वॉइस ऑफ द से कुछ उनको पूछना है या प्रेस के लिए प्रेस रिलीज के लिए आपने उनका कार्यक्रम देखा है शायद अभी भी आप उसी तरह से इस मैरी को रखेंगे। और मैं कहना चाहूंगा कि हमारे महात्मा गांधी कहा करते थे कि when passage is lost the war is lost, when passage is lost the war is lost। तो पैसेज अपने को बनाए रखेंगे और इस गाड़ी को आगे बढ़ाने की चेष्टा करते जा रहे हैं और इसी कड़ी में वेलकम एड्रेस होगा हमारे साहरसा गवर्नमेंट। वेलकम।
हेलो अपने विश्वविद्यालय के और विश्वविद्यालय से आए और दर्शक के मामले में सभी श्रोता विगत साथी एक साथ मैं आप सबका हार्दिक स्वागत करता हूँ, अभिनंदन करता हूँ और एमएलटी कॉलेज सहरसा के स्कूल पर आज एक उत्सव का माहौल है, एक सुखद क्षण है जिनकी स्मृतियां विगत कई वर्षों से जिनकी माननीय कुलपति महोदय, माननीय कुलपति महोदया और विश्वविद्यालय के तमाम अधिकारियों से प्राप्त प्रेरणा के आलोक में और आप सभी सारस्वत निर्भर जन के द्वारा दिखाए गए मार्ग पर चलकर मेरा यह कार्यक्रम इस मंजिल तक पहुंचा है, समापन को मैं सर्वप्रथम अपने विश्वविद्यालय के यशस्वी कर्मठ और निरंतर कार्य साधना में लगे रहने वाले कुलपति प्रोफेसर डॉक्टर आभा सिंह जी को नमन करता हूँ, वंदन करता हूँ, अभिनंदन करता हूँ और स्वागत करता हूँ। इस मंच पर बैठे हुए मेरे दुआएं और गाने को जो विभूति है प्रोफेसर डॉक्टर नवीन कुमार जी जो भौतिक विभाग के अध्यक्ष हैं और भौतिक विभाग के विभागाध्यक्ष भी हैं और मेरी गाड़ियों मेरे प्रोफेसर डॉक्टर राजकुमार सिंह जी ये सोशल साइंस के सामाजिक विज्ञान के संकाय अध्यक्ष हैं और लेखनी के बहुत ही धनी और बहुत ही धनी है। मैं इन दोनों का सादर अभिनंदन करता हूँ और इस सेमिनार इस कॉन्फ्रेंस में पढ़ाने के लिए मैं इन्हें साधुवाद दे रहा हूँ। मेरे बगल में बैठे हुए हैं केंद्रीय विश्वविद्यालय मोतिहारी से समागत देवव्रत चतुर्वेदी जो आज के सेशन के लिए प्रमुख वक्ता हैं, इनको भी मैं बहुत साधुवाद देता हूँ, इनका आभार व्यक्त करता हूँ और नमन भी करता हूँ। पानी और उपस्थित हैं, ये भी स्पीकर है यहाँ पे और रिपोर्टर भी के रूप में ये स्वागत है विश्वविद्यालय से। मैं इसका भी हार्दिक अभिनंदन और नमन करता हूँ। मेरे सामने जो बैठे हुए हैं मेरे प्रेरणा स्रोत कॉलेज मधेपुरा के यशस्वी प्रधानाचार्य जब मुझे कहीं किसी बात की जरूरत होती थी मैं सर को फोन कराता था और ये निरंतर मेरा काम करते रहे। इसके लिए मैं इन्हें भूरिशः शतशः कोटिशः धन्यवाद और आभार। सामने बैठे हुए हैं मेरे भाई अग्रज जी हैं प्रोफेसर डॉक्टर अरुण कुमार बाबू आनी जवाहरी कॉलेज के आचार्य हैं। इनकी जरूरत मुझे तब पड़ती है कि जब कहीं पेज फंस जाता है तो इनको जब मैं टेलीफोनिक बात कर देता हूँ तो सारी समस्या हमको के पास होती है और ये समाज में उसके मैं काफी संतोष देता हूँ और कहता हूँ उनके बगल में बैठे हुए अभी जो मित्र हैं समझ हैं और विश्वविद्यालय के विकास पदाधिकारी के पद पर हैं, ये विशेष आभार के उसके अशोक कुमार बाबू, रंजीत बाबू, पूर्व प्रधानाचार्य पीयूष बाबू, इन सबों का मैं हार्दिक अभिनंदन करता हूँ। मेरे सामने मैं देख रहा हूँ रमेश बाबू को और अरुण बाबू को, ये दोनों विभागाध्यक्ष हैं अपने अपने विभाग के और खास करके रहते हैं और जब कभी भी उन दोनों की बातें होती हैं मैं इन दोनों विभूतियों को भी नमन करता हूँ। इस सेमिनार पंजाब में उपस्थित मेरे महाविद्यालय के और अन्य महाविद्यालय के शिक्षक बंधुओं, मैं सादर समर्पित हूं के लिए कि जो संभव हो सकेगा मैं उनके लिए करता हूं। और इस समायोजन को, इस कॉन्फ्रेंस को, इस सेमिनार को सुसज्जित करने में, कार्य देने में इन लोगों का जो योगदान है यह नमस्कार है। इसलिए ये सारे के सारे मेरे प्रणम्य हैं। मेरे दर्शक की राह में बैठे हुए हैं मेरे शिक्षा संकाय के बहुत सारे अध्यापक जो अपनी प्रतिभा से, अपने पाठ कौशल से विषमता में भी, विषमताओं में भी संतुलन पैदा कर देती है। मैं उन लोगों का भी स्वागत करता हूँ। विभिन्न विश्वविद्यालयों से समाज शोधार्थी और शिक्षकगण जिन्होंने इस कॉन्फ्रेंस में भाग लिया है, मैं उन लोगों का आभारी हूँ। उन लोगों ने इस कॉन्फ्रेंस में कराने के लिए, इसको व्यवस्थित करने के लिए एक दशा दी, एक दिशा भी दी और मैं उसी पर काम रहा हूँ। मैं विशेष रूप से आभारी हूँ अपने मीडिया वालों को जिन्होंने लास्ट में से कवर किया और करने की चेष्टा कर रहे हैं। अंत में मैं विशेष रूप से उन सभी सहयोगियों का जिन्होंने जीतों परिश्रम करके इस सेमिनार को इस मुकाम तक, इस मंजिल तक पहुंचाया है, मैं उनका आभारी हूँ। और विशेषकर संजीव जी, आनंद जी, के राज जी, विपिन जी, अखिलेश कुमार जी, सौरभ साहब और अन्य सबों ने भरपूर सहयोग और मेरी सहायता की। इसके लिए ये सभी साधुवाद के योग्य हैं। मैं इनका भी भूरी भूरी अभिवादन करता हूँ। समय की गरिमा को दृष्टिपथ में रखते हुए मैं अपने कर्तव्य को विश्राम देना चाह रहा हूँ ताकि आगे का कार्यक्रम बढ़ता रहे। इसी के साथ मैं देता हूँ अपनी वाणी को।
मैं आज के इस कॉन्फ्रेंस के जो मॉनिटर हैं सभी को मैं उनसे आग्रह करता हूँ कि वो यहाँ आ जाए, तस्वीर लाए और आप इमर्जिंग साइंस एंड टेक्नोलॉजी उसके मुख्य थीम उस पर
बहुत बहुत धन्यवाद शिशिर सर। सब गोटे के स्वागत करे छिए। विशेष रूप से मंच पर उपस्थित बीएन मंडल विश्वविद्यालय के प्रतिकुलपति महोदय प्रोफेसर साहरसा सिंह मैडम का वेलकम यू ऑल। I want to convey my heartfelt gratitude to the patron, Honorable Pro Vice Chancellor, BN Mandal University, Madhepura, Professor Saharsa Singh Ma'am, for accepting the invitation and gracing the occasion by presiding over this international conference on emerging trend in science and technology. I am grateful to the keynote speaker of today's inaugural session, Professor Jagdat Chaturvedi sir, Head School of Physical Science, Mahatma Gandhi Central University, Motihari. I welcome Dean Faculty of Science, Professor Naveen Kumar sir. I welcome Dean Faculty of Social Science, Professor R.K. Singh sir. And I welcome all the principals here, Professor K.P. Yadav sir, Professor Arun Kumar Khan sir, Professor Ashok Kumar Singh sir, for their all kind of support, which was very crucial for the grand success of this seminar. And also I welcome the PG head, Professor Arun Kumar sir, and Professor Ranjit Kumar Singh sir, Professor Ramesh sir, and one name I am missing, Professor Sanjeev Kumar sir, Principal BSS College Support, which has given me all kind of support for this seminar. Before we begin this seminar, I would like to express my heartfelt gratitude to all esteemed teachers, research scholars, who are sincerely committed to this event to make it a success. This event would have been impossible without the support of each and everyone present here. It is hard to imagine our life now without science and technology. Indeed, our existence itself depends on it now. Every day, new technologies are coming up, which are making human life easier and more comfortable. Thus, we live in an era of science and technology. Science and technology have also made an impact on the medicine and agricultural fields. The various cures being discovered for diseases which have saved millions of lives through the science. The latest example is COVID vaccine, which saved millions of lives in India and abroad. Moreover, technology has enhanced the production of different crops, benefiting the farmers largely. Information and communication technology, especially for the teaching and learning. Environment, energy, climate change, biotechnology, drug design, robotics, artificial intelligence, cloud computing are the major area of research. Scientific and technological advancement of our country have enhanced the economy of the world and of the India. Subsequently, the science and technology have assisted in advancing various fields, including mathematics, astrophysics, space technology, nuclear energy, and more. So I believe that why not take this opportunity to organize a seminar on the role of scientific research. I am sure that the participant here will enrich a lot with the shower of esteemed speakers in this concerned community. I am sure that faculties and scholars will find a new domain in the contemporary research, and that will certainly open new ways to enhance the scientific outcome. Once again, I welcome all the participants on the behalf of organizing committee, MLT College Saharsa. Thank you all.
धन्यवाद हमारे रविंद्र साहब ने अति संक्षेप में आज के इस विषय के थीम आपके समक्ष रखा और एक बात मैं कहूं कि हमारे रिसर्च कॉलेज बोर्ड से हमारे संजीव कुमार उनके स्वागत मैं डॉक्टर रमेश कुमार सिंह जी को आमंत्रित करता हूं कि वो अपने कुर्सी से उठकर डॉक्टर संजीव कुमार झा प्रिंसिपल बीएसएस कॉलेज को का स्वागत फूलमाला और चादर बीएसएस कॉलेज को के विश्वविद्यालय का स्वागत करते हैं। इस महाविद्यालय में तो ये एक सेमिनार बहुत ही चिर प्रतिष्ठित था, लॉन्ग अवेटेड इस एमएलटी कॉलेज में एमएलटी महाविद्यालय बहुत दिनों से और हम लोग कुछ हिम्मत भी करते थे, फिर हिम्मत हार जाते थे। ये बहुत बड़ा आयोजन है और इससे हम सफल हो पाएंगे। मुझे हरिवंश जी की बात बड़ी याद आती है, उन्होंने बहुत ही अच्छा लिखा कि लहरों के डर से नैया पार नहीं होती, लहरों के डर से नैया पार नहीं होती, कोशिश करने वालों की कभी हार नहीं होती। मैं इसलिए अब कार्यक्रम को आगे बढ़ा रहा हूं और अब बारी है रिलीज ऑफ सॉवरेन को आया जाए और
ऑफ टाइम हो जाता है।
अब हम लोग सावनेर के विमोचन के लिए प्रस्तुत हो चुके हैं। इस इंटरनेशनल कॉन्फ्रेंस के लिए जो प्रस्तुत है सावनेर, उसके विमोचन। सावनेर का विमोचन हुआ। हमारे अतिथिगण बारी बारी से इस विलंब से आ ही रहे हैं। आरजीएम कॉलेज सहरसा से इस सभा में उपस्थित हुए हैं हिंदी विभाग के डॉक्टर के श्रीवास्तव साहब। मैं आग्रह करता हूं अपने कन्वेनर से कि उनका हार्दिक अभिनंदन, उनका अभिनंदन फूल माला से किया जाए। और बगल में हमारे मित्र बैठे हुए हैं डॉक्टर सुनील चंद्र मिश्रा जी, वही मैं उन्हीं से आग्रह करता हूं कि बगल में है और वो फूल माला से श्रीवास्तव जी का स्वागत करें। डॉक्टर सुनील चंद्र मिश्रा अंग्रेजी विभाग एमएलटी कॉलेज सहरसा के द्वारा आरजीएम कॉलेज के हिंदी विभाग के विभागाध्यक्ष श्रीवास्तव साहब का स्वागत करते हैं। डॉक्टर सुनील चंद्र मिश्रा। मैं थोड़ा सा इसमें करेक्शन कर देता हूँ कि हमारे श्रीवास्तव साहब और इसी सेक्टर में आकर के हेड बने हैं, तो थोड़ा सा मैं चूंकि उनको उसी रूप में जानता था कि वो आरजीएम कॉलेज सहरसा में ही है, तो मैं इसके लिए क्षमा कराना चाहता। अब यह कार्यक्रम आगे बढ़ रही है। हमारे जो मंच पर आसीन अतिथिगण है, विशिष्ट अतिथिगण, विशिष्ट मेहमान, उस कड़ी में मैं सबसे पहले आग्रह करूंगा डीन सोशल साइंस प्रोफेसर डॉक्टर आरके सिंह साहब का कि वो इस स्थान पर उपस्थित हो और हमें 2-4 मिनटों में अपने संबोधन से अभिभूत करें। डॉक्टर आरके सिंह, डीन सोशल साइंस।
इस 2 दिवसीय अंतर्राष्ट्रीय सम्मेलन के आयोजन में उद्घाटन सत्र में मंच पर उपस्थित बीएन मंडल विश्वविद्यालय की प्रसिद्ध कुलपति महोदया प्रोफेसर डॉक्टर आवा सिंह जी, सेंट्रल यूनिवर्सिटी मोतिहारी से आए हुए विषय विशेषज्ञ, इस महाविद्यालय के प्राचार्य देवानंद जी, उनके बगल में बैठे हमारे विश्वविद्यालय के विज्ञान संकाय के संकायाध्यक्ष नवीन बाबू, और उनके बगल में ऐसे दूसरे मिथिला विश्वविद्यालय से आए विज्ञान के विषय विशेषज्ञ, मंच के ठीक सामने बैठे विभिन्न महाविद्यालयों के प्रधानाचार्य, विश्वविद्यालय से आए विज्ञान के विभागाध्यक्ष, पीजी सेंटर से आए हुए हमारे करीब सहरसा कॉलेज के सभी शिक्षक, शोधार्थी, छात्र एवं छात्राएं, मुझे पता नहीं क्यों सबसे पहले बुला लिया गया। मैं बाद में आना सोच रहा था, बाद में इसलिए कि जब साइंस के लोग बोल लेंगे तो उन्हीं में से कुछ बातें निकाल कर मेरा भी काम चल जाए, लेकिन ऐसा हुआ नहीं। और जो एंकर महोदय है, उन्होंने मेरे लिए समय 2 से 4 मिनट का दिया, तो जैसे ही उन्होंने कहा 2 से 4 मिनट, तो मैं कंफ्यूज हो गया कि मैं 2 मिनट बोलूं, 4 मिनट बोलूं या 6 मिनट बोलूं। 2 और 4 को जोड़ देंगे तो 6 हो जाए। अब यह निर्णय मैं आप पर छोड़ता हूँ, ऐसे क्योंकि मैं विज्ञान विषय का नहीं हूँ, समाज विज्ञान का हूँ, लेकिन मैं प्रधानाचार्य महोदय को इस बात के लिए विशेष रूप से धन्यवाद देना चाहूंगा कि यह जो इस कॉन्फ्रेंस का आयोजन जो किया गया है, इसके लिए जो टॉपिक चुना गया है और जिस तरह से इसे उपस्थित किया गया है, तो यह सिर्फ विज्ञान का विषय नहीं है। पढ़ने के लिए साइंस है, टेक्नोलॉजी है, बहुत सारे विषय के शिक्षक यह सोच कर नहीं आए कि यह तो विज्ञान का है, आर्ट वाले, कॉमर्स वाले इस पर जाके क्या करें। लेकिन मेरा यह मानना है कि समाज और विज्ञान दोनों अलग अलग नहीं है। विज्ञान में जितने सारे रिसर्च होते हैं, सब सामाजिक समस्याओं को ध्यान में रखते हुए किए जाते हैं। उनका प्रभाव भी समाज पर पड़ता है, व्यापक रूप में पड़ता है, और खासकर आज हम जिस युग में जी रहे हैं, यह तो हम सब विज्ञान के बिल्कुल करीब हो गए हैं। हमारे आपके पॉकेट में रुपया हो भी सकता है, नहीं भी हो सकता है, लेकिन एक छोटा या बड़ा मोबाइल जरूर है, और यह मोबाइल जो है कहीं न कहीं विज्ञान की देन है, और विज्ञान से विकसित किए गए टेक्नोलॉजी का यह कमाल है कि यह आज कोई मेरे साथ नहीं रहता है। जब मैं अकेला रहता हूँ तब इससे अच्छा कोई टाइम पास का इंस्ट्रूमेंट हमारे पास नहीं है।
आप सब लोग सोशल मीडिया पर जागरूक हैं। हर परिवार में इसके कारण तनाव है, लोग दुखी हैं कि परिवार का अमुक सदस्य मोबाइल पर बहुत समय देता है या परिवार में झगड़े का कारण है। खासकर उस परिवार में भी जिसमें सिर्फ पति पत्नी ही रहते हैं, 2-3 बार झड़प हो ही जाती है कि मोबाइल में क्या देखते रहते हैं। तो इसलिए यह इतना कॉमन है, अब कॉमन ही नहीं, इसने हमारे लाइफ को पूरी तरह से प्रभावित किया है। हमारी स्वतंत्रता इसने छीनी है, हमारी प्राइवेसी को इसने खत्म किया है, परिवार समाज में तनाव आया है। इसलिए आज जो हमारे सामने चैलेंज है, चैलेंज विज्ञान के सामने भी है और चैलेंज समाज के सामने भी है। आज विकास की दृष्टि से हम चौथे दौर में चल रहे हैं। पहला दौर में जो औद्योगिक रिवॉल्यूशन हुआ तो उसमें वाटर और स्टीम पावर का बोलबाला रहा। दूसरे फेज में इलेक्ट्रिक पावर का बोलबाला रहा। तीसरे फेज में इंफॉर्मेशन टेक्नोलॉजी का और इलेक्ट्रॉनिक्स का बोलबाला रहा। और आज यह जो चौथा फेज है, जो डिजिटल रिवॉल्यूशन भी कहा जाता है, तो उसमें हम आप जी रहे हैं। आज हमारे सामने रोबोट्स आने लगे हैं, नैनो टेक्नोलॉजी की बात होने लगी है, आर्टिफिशियल इंटेलिजेंस की बात होने लगी है और आने वाले समय में इनके कारण जो खतरे हैं उसे विज्ञान को भी बचना है और समाज को भी बचाना है। अब वह समय दूर नहीं है जब हम वैसी टेक्नोलॉजी बना लेंगे जिस पर हमारा कोई नियंत्रण नहीं होगा। अब तक जो भी टेक्नोलॉजी बनी है उस पर हमारा नियंत्रण है, लेकिन आने वाले समय में ऐसी टेक्नोलॉजी आ रही है जिस पर हमारा वैज्ञानिकों का कोई नियंत्रण नहीं रहेगा। वह सब कुछ अपने मन से करेगा, अपनी समझ से करेगा। तो वह एक मानवता के लिए या विज्ञान के लिए भयानक स्थिति होगी। और मैं इसमें इस बात को भी जोड़ना चाहूंगा कि हम आप महाविद्यालय के शिक्षक हैं, विश्वविद्यालय विभाग के शिक्षक हैं, तो अगर अपने सिलेबस पर हम एक नजर डालें तो हमें पता चलेगा कि आज विज्ञान कहाँ है, टेक्नोलॉजी कहाँ है और हमारा सिलेबस कहाँ है। हम बहुत पीछे हैं। आज एजुकेटेड लोगों की कमी नहीं है समाज में, वैसे लोगों की भी कमी नहीं है जिनके पास ढेर सारी डिग्रियां हैं। हमको तो लगता है कि आज मैट्रिक पास करने से ज्यादा सस्ता है पीएचडी कर लेना, कम मेहनत में। खर्च की बात मैं नहीं कर रहा हूँ, मेहनत की बात कर रहा हूँ। मेहनत कुछ नहीं है, खर्च चाहे लाखों में हो जाए, वो तो उसकी किस्मत पर है कि कितने मौजूद हो जाए। अब हम एजुकेटेड भी हैं, प्रमाण पत्र भी मेरे पास बहुत है, बहुत ऊंचे ऊंचे अंक का प्रमाण पत्र भी मेरे पास है, लेकिन मेरे पास 2-3 चीजें नहीं है। मेरे पास नॉलेज की कमी है, नॉलेज नहीं है। नॉलेज अगर है भी तो उसका एप्लीकेशन साइंस और टेक्नोलॉजी के इतिहास से हमने करना नहीं सीखा है। नॉलेज है लेकिन लर्निंग नहीं है, उसका उपयोग हम नहीं जानते हैं। चाहे स्किल लेवल की बात हो, बड़ी टेक्नोलॉजी की बात हो, तो इसलिए उस मामले में हमारी जो शिक्षा व्यवस्था है वह काफी पीछे है। हम तो जहाँ है, जिस प्रदेश में है, मुझे लगता है कि 30-40 साल पहले साइंस के लेबोरेटरी का ताला खुला करता होगा, क्योंकि मेरी भी सेवा 35-40 साल की हो गई। शुरू के 5-7-10% को अगर छोड़ दिया जाए तो 90-88-90 के बाद बिल्कुल बंद है। और वैसी स्थिति में आप यह कल्पना कीजिए कि इन 30 वर्षों में विज्ञान कहाँ गया, जिसको हम मेटा साइंस करते हैं, उसके कारण विज्ञान कितना आगे गया, टेक्नोलॉजी कितनी आगे गई। आज हमारे आपके हाथ में एक मोबाइल आता है और एक सप्ताह के अंदर पता चलता है कि किसी कंपनी ने दूसरी मोबाइल बना ली, उसी कंपनी में नहीं भी बनाई तो दूसरी किसी कंपनी ने बना ली। अब हमारे हाथ में जो मोबाइल है वो पुराना हो गया। जहाँ टेक्नोलॉजी इतनी तेजी से बदलती है विज्ञान की कृपा से या उसके शोध से, तो जहाँ हमारा देश इतना पीछे है, कोई इन्वेस्टिगेशन नहीं होता, कोई वेरिफिकेशन नहीं होता, कोई डाटा कलेक्शन नहीं होता, कोई एक्सपेरिमेंट नहीं होता, फिर हम क्या उम्मीद करें। इसलिए यह जो टॉपिक है यह अपने आप को परखने के लिए भी है कि हम इस रेस में कहाँ हैं, हमारी शिक्षा व्यवस्था कहाँ है। और जब तक यह अपडेट नहीं होगी तब तक हमारे आपके बीच में बेरोजगारों की फौज खड़ी होती रहेगी। हम कुछ नहीं कर सकते हैं। सरकार नियोजन कर सकती है, आरक्षण दे सकती है, जो उसके हाथ में है, लेकिन ये जो मास एम्प्लॉयमेंट की बात है, चाहे वो स्किल्ड लेबर हो, अनस्किल्ड लेबर हो या हायर क्लास की टेक्नोलॉजी को चलाने की बात हो, तो उसके उस मामले में जो हमारी शिक्षा व्यवस्था है वह बिल्कुल फेल है। इसलिए लोग बेरोजगार भी होते हैं और पढ़े लिखे भी होते हैं। एक दूर की वैकेंसी होती है तो बहुत पीएचडी डिग्री वालों को नौकरी नहीं मिलती है, यह स्थिति है। तो इसलिए इस पर सोचने की जरूरत है, गंभीरता से सोचने की जरूरत है। आने वाले समय में तो हमारा नॉलेज भी है। अब देखिए नॉलेज की क्या किस्मत है। एक समय में नॉलेज हुआ करता था, लोग उससे भय खाते थे, इसके पास बहुत ज्ञान है। उसके बाद कहा गया कि नॉलेज इज पावर, और आज यह कहा जाता है कि नॉलेज एक कमोडिटी है, एक कमोडिटी है, वस्तु है। जिस तरह से कोई कंपनी अपनी वस्तु को आपके सामने एडवर्टाइजमेंट के माध्यम से उसे सजा कर, सवाल कर आपके सामने प्रस्तुत करती है, उसी तरह से आपको अपने नॉलेज को भी उस तरह से अपडेट करना होगा, साइंटिफिक तरीके से उसको फुल प्रूफ करना होगा, और तब उस नॉलेज का महत्व आपके लिए होगा। नॉलेज जब कमोडिटी हो गए, नॉलेज नहीं रहा, तो वैसी स्थिति में हमारे आपके पास जो थोड़ा ज्ञान है, बहुतों के पास नहीं है, कुछ लोगों के पास थोड़ा है, तो उसे भी प्रेजेंट करने का, समाज को दर्शाने का जो हमारा तरीका है, उसके लिए टेक्नोलॉजी का सहारा लेना होगा। और वह तब होगा जब हम उस टेक्नोलॉजी के बारे में जानेंगे, उसे हम चलाना सीखेंगे, और उसके बारे में जितना अधिक जानेंगे उतना हमें लगेगा कि हम कुछ नहीं जानते, बहुत कम जानते। अब जानने का जहाँ पर सवाल है, तो अब यह स्पर्धा की बात नहीं है कि आप कम जानते हैं, आपसे हम ज्यादा जानते हैं। अब तो गूगल सबसे अधिक जानकार हो गया। हमको आपको अगर कोई बात नहीं समझ में आती है तो हम तुरंत उसको गूगल से पूछते हैं, गूगल बता देता है। तो अब तो सबसे ज्यादा नॉलेज वाला गूगल हो गया। इसलिए अब यह समस्या नहीं है कि आपसे हम ज्यादा जानते हैं, जब सबसे अधिक जानने वाला
मुझे हमारे बाईं ओर में आरएम कॉलेज के में प्रिंसिपल और मेरे बड़े भाई डॉक्टर अरुण कुमार खां, उसके बगल में मेरे मित्र प्रोफेसर ललन अदरी और एसएनएसआरपीएस कॉलेज के प्रिंसिपल प्रोफेसर डॉक्टर अशोक कुमार सिंह जी और मेरे मेरे महाविद्यालय, जिस महाविद्यालय से मैं आता हूँ उस महाविद्यालय के सेवानिवृत्त प्रिंसिपल प्रोफेसर पीएन पीयूष, इसके बाईं ओर बैठे हुए हैं हमारे इस कॉलेज के विभागाध्यक्ष रंजीत बाबू और मेरे भाई सदृश मेरे सीपी सिंह साहब, जो मुझे हर समय हर वक्त सलाह देते थे अच्छी अच्छी बातों के लिए, और मैं उनका हर सलाह को मानता था जब मैं था, जब समय परीक्षा नियंत्रक था। और इस साइड में मैं आ रहा हूँ, मैं सुनील चंद्र मिश्रा साहब का मैं बहुत बहुत अथी करता हूँ। जब ये पीजी हेड रहते थे तो मेरी इनसे बहुत सब में इनसे बातें होती रहती थी। और हिंदी के आरएजीएम कॉलेज के विभागाध्यक्ष साहब, उसको भी मेरा नमस्कार। उसके बाईं और हमारे एक मित्र हैं विपिन बाबू, जो फिजिक्स के ही हैं, उनको मैं नहीं देख रहा हूँ। और मैं एक आए हैं इंजीनियरिंग कॉलेज के प्रिंसिपल, एमआईटी कॉलेज के, वो बैठे हुए हैं, उनको भी मैं यहाँ स्वागत करता हूँ। यह 2 दिवसीय सेमिनार इमर्जिंग ट्रेंड इन साइंस एंड टेक्नोलॉजी के संबंध में मैं विस्तृत से जानकारी आपको विषय विशेषज्ञ देंगे, लेकिन मैं फिजिक्स का प्रोफेसर हूँ और फिजिक्स के प्रोफेसर के दृष्टिकोण से मैं 2-3-4 शब्द इनके संबंध में ही बोलना चाहूँगा। वैसे फिजिक्स, केमिस्ट्री, जूलॉजी और बॉटनी, और जहाँ तक पूर्व वक्ता हमारे राजकुमार बाबू ने विज्ञान को आर्ट्स फैकल्टी समाज से जोड़ के बताई, ये बहुत बड़ी बात बताई। और भौतिक शास्त्र में विज्ञान का जो योगदान हुआ है, इसमें जो भौतिक शास्त्र में जो इस ट्रेंड में जा रहा है, इसमें बहुत सारे शोध कार्य चल रहे हैं। जैसे एडवांस कंप्यूटिंग पर चल रहा है, सुपर कंप्यूटर का विकास होने जा रहा है, सुपर कंप्यूटर के विकास होगा। इलेक्ट्रॉनिक्स के क्षेत्र में कंडेंस और सेमीकंडक्टर को विकसित किया गया है। और उसके बाद टेक्सटाइल इंजीनियरिंग के क्षेत्र में नैनो माइक्रोफिकेशन का अध्ययन किया गया है। इतनी बात के बावजूद भी ये नैनो, एक चीज और मैं आपको स्पष्ट रूप से बता देना चाहता हूँ, नैनो पर भारतीय विज्ञान में नैनो प्राधिकरण न्यूरो फिजिक्स, मनोभौतिकी और खगोलीय भौतिकी में के बारे में बहुत सारे विशेषज्ञ बताएंगे। आधुनिक जगत में विकास को ऊंचे शिखर पर पहुंचाया है और वैज्ञानिक ने नए खोज कर आज हमारे सभी कार्य को सुदृढ़ के आसान कर दिया है। नैनो प्राधिकरण के बढ़ते प्रभाव के चलते एक छोटी सी चिप्स से भी हम बड़े बड़े मशीनों को बैठे बैठे कंट्रोल कर सकते हैं। और रसायन शास्त्र में भी, जंतु विज्ञान में भी, प्लांट्स के क्षेत्र में भी, दवाइयों के क्षेत्र में भी, ये सब कैंसर के इलाज के क्षेत्र में भी साइंस, इमर्जिंग ट्रेंड ऑफ साइंस एंड टेक्नोलॉजी का विस्तार, ये विज्ञान से हमारे समाज को, हमारे देश को ऊंचाई और शिखर पर पहुंचा सकता है। आज भारत इस ऊंचाई की ओर बढ़ रहा है, अभी चौथे स्तंभ की ओर बढ़ गया है। यहाँ का नहीं कहा जा सकता है, अब मेरा भारत साइंस और टेक्नोलॉजी में बहुत आगे की ओर बढ़ा है। और इसके कारण है हमारे शोधार्थी, हमारे वैज्ञानिक, हमारे साइंटिस्ट। और यह सेमिनार हमारे शोधार्थी जो शोध कार्य कर रहे हैं वह नए ट्रेंड के लिए, उनके लिए एक अद्भुत चीज है। यह इस तरह के शोधार्थियों के लिए एक प्रेरणादायक चीज है। यह एक टॉपिक, बड़ा ही अच्छा टॉपिक करके यहाँ आज सेमिनार हो रहा है। सेमिनार मैं आज इस विश्वविद्यालय में, जहाँ तक पढ़ाई की बात में हमारे पूर्व वक्ता ने बोले कि पढ़ाई की अच्छी घट चुकी है, तो हम मान रहे हैं, लेकिन अगर हमारे शिक्षक चाहेंगे कि हम पढ़ाएंगे और विद्यार्थी में एक ललक पैदा करेंगे, अगर हमारे लैब में जा करके हमारे रिसर्च स्कॉलर से काम कराएंगे तो ये कहना बहुत आसान होगा कि काम नहीं, काम हो गई। हमारे बहुत विद्वान प्रोफेसर बीच में बैठे हुए हैं, मैं इतना ही कहूँगा। और विषय विशेषज्ञ आए हुए हैं, वक्ता हैं, उनकी बात को सुने और इस पर अच्छी करें। मैं इतना ही कह के मैं अपना आनंद करता हूँ।
अब स्टडी में जो प्रबोधन होना है वो बीएन मंडल विश्वविद्यालय के कृति कुलपति वाइस चांसलर मैडम से मैडम से आग्रह करता हूँ, निवेदन करता हूँ कि वो इस विषय पर अपने सारगर्भित संबोधन हम लोगों के बीच दें। डॉक्टर आवश्यक
सम्मानित मंच एवं सम्मानित सभागार, आज इस 2 दिवसीय अंतरराष्ट्रीय सम्मेलन के अवसर पर मैं सबसे पहले एमएलटी कॉलेज सहरसा के शिक्षकों, छात्रों, कर्मचारियों को यह बधाई देना चाहती हूँ, यह संदेश देना चाहती हूँ कि आपने ऐसा लीडर पाया है प्रधानाचार्य के रूप में, जिन्होंने अपने कार्यकाल के 4-5 महीने के अंदर ही इस प्रकार के सम्मेलन को आयोजित करने का बीड़ा उठाया और उससे सार्थकता प्रदान की। इस प्रकार के सम्मेलन का शिक्षा के क्षेत्र में अत्यंत महत्वपूर्ण स्थान होता है, जिसे शायद आज कल की शिक्षा व्यवस्था में थोड़ा विस्मृत कर दिया गया है। थोड़ा मैं इसलिए कह रही हूँ क्योंकि ऐसी बात नहीं है कि सभी लोगों ने इसे भुला दिया है, भरसक प्रयत्न होते रहते हैं, लेकिन यहाँ पर बीएन मंडल विश्वविद्यालय में विज्ञान संकाय में इस प्रकार का अधिवेशन करना मैं समझती हूँ महाविद्यालय के लिए तो उपलब्धि है ही है, हमारे विश्वविद्यालय के लिए भी उसकी उपलब्धियों में एक अमूल्य कड़ी के रूप में काम करेगा यह सम्मेलन। लेकिन मात्र सम्मेलन का आयोजन जिन लोगों के मेहनत से हुआ, जिन लोगों ने, सम्मेलन तो 2 ही दिन का है, लेकिन महीनों की नींद उड़ी होगी कुछ लोगों की, लेकिन वह सही मायने में सार्थक तभी होगा जबकि प्रतिभागी गण गंभीरता पूर्वक यहाँ पर विषय विमर्श करेंगे और कुछ सार्थक बातें उभर कर सामने आएंगी और जिससे हम सभी अवगत होंगे। क्योंकि बंद कमरे में बैठ कर के कुछ बातें कर लेना वो उपलब्धि नहीं होती है जब तक कि उस उपलब्धि का प्रभाव समाज पर न दिखे। अब इस अधिवेशन का सीधा संबंध, अधिवेशन का विषय जो है, ट्रस्ट एरिया जो है, इमर्जिंग ट्रेंड्स इन साइंस एंड टेक्नोलॉजी, तो साइंस एंड टेक्नोलॉजी के कमाल से तो हम सभी परिचित हैं, और साइंस एंड टेक्नोलॉजी का ही कमाल था कि कोरोना जैसी महामारी पर बहुत कम समय में विजय प्राप्त की गई। उस काल में जबकि संपूर्ण विश्व एक प्रकार से कहा जाए कि शिथिल हो गया था, किंतु इसी टेक्नोलॉजी ने विश्व को, ये जरूर था कि हमारे दिनचर्या में डायनामिज्म नहीं था, हम लोग घर से बाहर नहीं निकलते थे, लेकिन मेंटल डायनामिज्म का घोर अवसर प्राप्त हुआ। इतना समय था कि मानसिक रूप से हम लोग पूरी तरह से सचेत होकर के जिसने भी चाहा उसने उपलब्धियां हासिल की। अब यह कहना अत्यंत साधारण बात है कि विज्ञान, ऐसा माना जाता है कि साइंस डिस्पैशनेट नॉलेज है, यानी कि साइंस में बिना किसी प्रिजुडिस के नॉलेज लक्ष्य होता है ज्ञान प्राप्त करना। और ज्ञान क्या होता है? ज्ञान वह होता है जो कि आत्मा को प्रकाशित करता है। और साइंस जिस प्रकार से नॉलेज हासिल करता है, उस नॉलेज का सीधा प्रभाव हमारे समाज के ऊपर पड़ता है। और साइंस की उपलब्धियों ने हमें यह दिखा दिया कि हमसे पहले 2 पीढ़ी पहले के जो हमारे पूर्वज थे, वह उस प्रकार की जीवन शैली को सोच भी नहीं सकते थे जिस जीवन शैली को आज हम लोग जी रहे हैं। तो कैसे? क्योंकि साइंस की जो उपलब्धियां हासिल हुई उसको टेक्नोलॉजी में परिणत करके आम जनता तक पहुंचाया गया। अब टेक्नोलॉजी में जब परिणत किया गया तो क्या होता है? टेक्नोलॉजी क्या चाहिए? टेक्नोलॉजी को आम जनता को तो सुख सुविधा देना ही है, लेकिन उसमें चाहिए कमर्शियलाइजेशन चाहिए, हमको कुछ फायदा होगा तभी तो उसका विस्तारीकरण करेंगे, जनता तक पहुंचाएंगे। और जहां पर कमर्शियलाइजेशन हो जाता है वहां पर पैशन आ जाता है, और जब पैशन आ जाता है तब उसमें गिरावट हो जाती है। अब साइंस और टेक्नोलॉजी, अब जब पैशन आ गया उसमें, तो क्या ये माना जा सकता है कि साइंस इज वैल्यू न्यूट्रल? क्योंकि साइंस को ही तो टेक्नोलॉजी में कन्वर्ट कर रहे हैं हम लोग। तो यहाँ इस बात पर ध्यान देने की आवश्यकता है कि साइंस और टेक्नोलॉजी दोनों ही ह्यूमन एक्टिविटीज हैं, और कोई भी ह्यूमन एक्टिविटी ऐसा नहीं होना चाहिए जो कि मानव के हित के प्रतिकूल हो। गीता में इसे लोक संग्रह कहा गया है। वही एक्टिविटी मानव की एक्सेप्टेबल है जिससे कि मानव का कल्याण हो। अब साइंस और टेक्नोलॉजी के बीच में एक बैलेंसिंग फैक्टर की आवश्यकता है, और वो बैलेंसिंग फैक्टर क्या हो सकता है और वो कहां से आएगा? तो मैंने बोला वैल्यूज। अब वैल्यू का जो मूल है वह कहाँ है? वह है आत्मा में, वह है स्पिरिचुअलिटी में जब वैज्ञानिक डिस्कवर करता है कुछ, तो होता है कि उसने रियलिटी को खोजा, अल्टीमेट रियलिटी के एक एस्पेक्ट को डिस्कवर किया। लेकिन ये एस्पेक्ट वाइज जो डिस्कवरी होती है, उससे नॉलेज कंपार्टमेंटलाइज हो जाता है, विभागीकरण हो जाता है। और जब विभागीकरण हो जाता है तो उस नॉलेज को अल्टीमेट नॉलेज कहना मुश्किल हो जाता है। अब देखिए कि हम जानते हैं कि साइंटिफिक डिस्कवरी कैसे होती है। सब्जेक्ट और ऑब्जेक्ट का डिस्टिंक्शन होता है। जो सब्जेक्ट है वो डिस्कवर करता है, लेकिन ये डिस्टिंक्शन जो है यह तब तक बना हुआ रहता है जब तक कि अल्टीमेट नॉलेज नहीं हो जाए। और अल्टीमेट नॉलेज जब होता है, देखिए आप ये जानते हैं कि न्यूटनियन जो विज्ञान कहा जाए, न्यूटनियन साइंस या कार्टेशियन सिद्धांत, कार्टेशियन सिद्धांत का नाम आपने सुना होगा। तो ये जो है वह जड़ और चेतन में वाटर टाइप डिस्टिंक्ट, एक जड़ जगत है और एक चेतन जगत है। चेतन जगत जो है वो जड़ जगत के बारे में उद्भेदन करता है, खोज करता है। लेकिन हमारे वैज्ञानिक जगदीश चंद्र बसु ने क्या किया, उन्होंने यह दिखला दिया कि जो जड़ है, सो कॉल्ड मैटर जो है, मैटर को भी अनुभूति होती है। ये जरूर है कि हम लोग जो सचेतन प्राणी हैं, जो अनुभूत करते हैं, उसको बहुत रिएक्शन हमारा विजिबल हो जाता है, लेकिन जड़ का रिएक्शन जो होता है वह धीरे धीरे दिखता है। अब जब हमारे वैज्ञानिकों ने यह प्रमाणित कर दिया है कि जड़ और चेतन में वास्तव में कोई ऐसा डिस्टिंक्शन नहीं है। हमारे वैदिक ऋषियों ने क्या ढूंढा था कि संपूर्ण जगत जो है उसकी निर्मिति हुई है पंचकोश से। चाहे वह अन्नमय कोश हो, जो कि इस जड़ जगत को हम देखते हैं, प्राणमय कोश हो, मनोमय कोश हो, आनंदमय कोश हो, जो कुछ भी हो, वो सब मिला करके यह जगत बनता है। तो ये 5 कोश जो हैं, यह मैटर से लेकर के स्पिरिट और सुपर माइंड की ओर जाते हैं और सुपर माइंड से लेकर के स्पिरिट की ओर आते हैं। यानी कि स्पिरिचुअल जो गहराई होती है, वहां पर जड़ और चेतन का भेद मिट जाता है। वहां पर इंटीग्रेटेड नॉलेज पैदा होता है। इंटीग्रेटेड नॉलेज में क्या होता है कि समस्त जगत एक दूसरे से कनेक्टेड है, और जहां पर इस कनेक्टिविटी का ज्ञान हो जाएगा, वही असल स्पिरिचुअलिटी है। और इस कनेक्टिविटी को समझते हुए विज्ञान के जो खोज है, विज्ञान की जो उपलब्धियां हैं, उनको टेक्नोलॉजी में जब रूपांतरित किया जाएगा, तो हमारा स्पिरिचुअल एस्पेक्ट उसमें मार्गदर्शन करेगा और तब विज्ञान का गलत प्रयोग नहीं होगा और विज्ञान का प्रयोग मात्र मानव कल्याण करने का मतलब मात्र मानव जीवधारी से ही नहीं है। कल्याण का मतलब है कि समस्त जगत के कल्याण के लिए होगा, क्योंकि आज हम जानते हैं कि विज्ञान की खोज जो है वह मानव केंद्रित है और मानव केंद्रित भी जो अमीर देशों के मानव हैं उनके लिए जो सूट करता है वही ज्यादा फ्लरिश करता है। गरीब देश के मानव के लिए कोई उतनी ज्यादा चिंता नहीं करता है। लेकिन विज्ञान का आधार, विज्ञान और टेक्नोलॉजी के बीच की खाई को यदि स्पिरिचुअलिटी से पाटा जाए तो निश्चित तौर पर हम विज्ञान के बारे में सोच सकते, विज्ञान ऐसा विज्ञान प्राप्त करेंगे जो सर्वजन हिताय होगा और सभी लोग ऐसे जगत का निर्माण होगा जिसमें सभी सुखी रहेंगे, सबका कल्याण होगा। इन्हीं शब्दों के साथ एक बार पुनः मैं आप सबों को धन्यवाद देती हूँ।
धन्यवाद वाइस चांसलर साहब मैडम को अपने इस भाषण के लिए। विज्ञान और स्पिरिचुअलिटी दोनों के बीच में जो एक संबंध होना चाहिए। Now we have the turn of vote of thanks. I would like to request Dr. Madhepura to come on the dais and pay vote of thanks to all of the guests and participants and the speakers.
सहरसा महाविद्यालय का संशोधित नाम एमएलटी कॉलेज सहरसा हुआ है, जो इस बीएन मंडल विश्वविद्यालय का सबसे पुराना महाविद्यालय है और शिक्षा जगत में इस महाविद्यालय को स्तंभ के रूप में जाना जाता है। आज इस महाविद्यालय में पहला एक दिवसीय अंतर्राष्ट्रीय सेमिनार आयोजित है, जिसमें हमारे संरक्षक, मुख्य संरक्षक प्रति कुलपति महोदया प्रोफेसर डॉक्टर आवासी, विशिष्ट अतिथि विज्ञान संघ के अध्यक्ष प्रोफेसर डॉक्टर नवीन कुमार और सामाजिक विज्ञान संघ के अध्यक्ष प्रोफेसर डॉक्टर राजकुमार सिंह जी मंचासीन है और इनका अभूतपूर्व सहयोग रहा है। और आज जो भी हो रहा है इन लोगों के सहयोग से ही इस सेमिनार का आयोजन किया गया है। और इस प्रसाल में उपस्थित हमारे विभिन्न महाविद्यालय के प्रधानाचार्य, शिक्षक एवं शोधार्थी सबों का स्वागत है, हार्दिक अभिनंदन है। और सबों से अनुरोध है कि आज जो हमारे विशिष्ट अतिथि हैं उनको सुनेंगे और साइंस एंड टेक्नोलॉजी के रिसेंट ट्रेंड्स पर कुछ ज्ञान वर्धन की बात होगी और उसमें इंटरेक्शन करेंगे। यही सबों से अनुरोध है कि इसके बाद के कार्यक्रम में आप लोग सभी सहभागी होंगे, यही आपसे अपेक्षा। जय हिंद।
अब शिफ्ट बदल रहा है। बिफोर लंच हमारे विशिष्ट अतिथि जो मोतिहारी सेंट्रल यूनिवर्सिटी से आए थे, यानी कि अभी टेक्निकल सेशन का फर्स्ट पार्ट शुरू होने जा रहा है।
दो अतिथि आएगा सिद्धार्थ सर्कल से इकोनॉमिक्स से, उनका स्वागत करवा दीजिए। और यादव जी प्रिंसिपल आया हुआ कॉलेज, उनका स्वागत से आप करवा दीजिए। बैठे बच्चे बराबर ठीक है।
इससे पहले इनको मैं मंच पर बुलाऊं, उनको मैं इस माइक्रोफोन के सामने बुलाऊं। उससे पहले हमारे बीच आर्यन लॉ कॉलेज के प्रधानाचार्य त्रिवेदी साहब आए हुए हैं और मैं डॉक्टर अरविंद कुमार यादव जी से आग्रह करता हूं कि वो फूल माला के साथ लॉ कॉलेज के प्रधानाचार्य जी का स्वागत करें। इकोनॉमिक्स के हेड डॉक्टर सिद्धार्थ शंकर सिंह जी का स्वागत हुआ है डॉक्टर अरविंद कुमार यादव जी के कर्मयों से। उनको सामने बैठे हुए हैं सर, सामने बैठे हुए हैं। डॉक्टर अरविंद कुमार यादव द्वारा इकोनॉमिक्स के हेड डॉक्टर एस.के. सिंह साहब का स्वागत। तालियों से स्वागत होनी चाहिए हमारे इकोनॉमिक्स के हेड साहब। कहाँ वही है? मनोज जी को बोलिए, मनोज जी को बोलिए। अजीत सिंह और हमारे आर्यन लॉ कॉलेज के प्रधानाचार्य जी के स्वागत के लिए मैं डॉक्टर अजय कुमार सिंह जी को आग्रह करता हूं कि उनका स्वागत बोलबाला से किया जाए। इस टेक्निकल सेशन में जो हमारे टेक्निकल सेशन फर्स्ट जो हमारे मुख्य वक्ता हैं वो है प्रोफेसर डॉक्टर देवदत्त चतुर्वेदी, प्रोफेसर एंड हेड डिपार्टमेंट ऑफ केमिस्ट्री, स्कूल ऑफ फिजिकल साइंसेज, महात्मा गांधी सेंट्रल यूनिवर्सिटी, मोतिहारी, बिहार। सर के हिस्से में या सर का एक बहुत बड़ा एकेडमिक प्रोफाइल है, मैं सबको तो नहीं पढ़ सकता, संक्षिप्त में बता देना चाहता हूं कि इनका जो रिसर्च का एरिया है वो है सिंथेटिक ऑर्गेनिक ऑब्लिक मेडिसिनल केमिस्ट्री। इन्होंने वर्ष 2003 में पीएचडी किया और ये फेलो है, पोस्ट डॉक्टरल फेलो है यूएसए एंड जर्मनी से। मोर देन 25 इयर्स ऑफ टीचिंग एंड रिसर्च एक्सपीरियंस इनके पास है, 25 वर्षों से ज्यादा का रिसर्च एक्सपीरियंस। 100 से ज्यादा पब्लिकेशंस इनका हो चुका है, नेशनल और इंटरनेशनल सेमिनार। और ये पेटेंट फील्ड्स में 11 पेटेंट करवा चुके हैं। पीएचडी थीसिस 10 के लगभग ये सुपरवाइज कर चुके हैं और एडिटोरियल बोर्ड्स के मेंबर हैं। 25 हाईली रेप्यूटेड इंटरनेशनल जर्नल्स के ये एडिटोरियल बोर्ड्स के मेंबर और 50 से अधिक इंटरनेशनल जर्नल्स के ये रिव्यू कर चुके हैं। इनके विषय में कई अवार्ड्स भी हैं, मैं उसको भी बता देता हूँ। यंग साइंटिस्ट अवार्ड 2008-9, हाईएस्ट इम्पैक्ट ऑफ द ईयर अवार्ड 2010, वर्क एज ए गेस्ट एडिटर फॉर पब्लिशिंग ए स्पेशल हॉट टॉपिक इश्यूड entitled ऑर्गेनिक सिंथेसिस यूजिंग ग्रीन रिएक्शन मीडिया इन द करंट ऑर्गेनिक सिंथेसिस
और अवार्ड डीएसटी फास्ट ट्रैक यंग साइंटिस्ट अवार्ड 2012, अवार्ड मोस्ट साइटेड पेपर अवार्ड 2006 और 9। इस हाई एकेडमिक प्रोफाइल से स्पष्ट है कि हमारे बीच एक ऐसे विद्वत व्यक्ति को आमंत्रित किया गया है जिनसे कि हमें इस टॉपिक पर काफी गहराई पूर्ण, जिसको हम रिकॉन्डाइट एक्सपीरियंस कहते हैं, रिकॉन्डाइट नॉलेज कहते हैं, वो हमें मिल सकता है। तो मैं आग्रह करता हूँ सर से, डॉक्टर डी चतुर्वेदी जी से, कि वो यहाँ आए और अपने विचारों से हमें अवगत करावे, हमारे ज्ञान का पथ।
मैं पार्टिसिपेंट्स से और हमारे जो कार्यक्रम अब मेडिकल सेशन का शुरू, उसमें वो
नहीं सर खराब है
Good afternoon to you all. Myself is Professor Devdutt Chaturvedi from Mahatma Gandhi Central University, Motihari. Respected Principal Sahab,
क्लोज कर लीजिए आवाज आ हाँ ये ठीक है दोनों ये भी ठीक है
deans of the science and the arts, principals of the various colleges, head of the departments and the deans of the schools of the various colleges and universities, research students and my dear research scholars. Today, actually, I am very much thankful to the organizing committee, particularly by Principal Sahab and the Department of Chemistry, especially Sanjeev Jha Sahab and Anand Mohan Jha, who has directly contacted me last 1 month back and asked me to come over here. And I used to be very much interested whenever somebody calls me for delivering a talk. Immediately I respond Anand Mohan Jha and ask him to fix my lecture here. So it is a very good opportunity for you all to listen my work here. I am thankful to all the organizing committee for inviting me here. The theme of the lecture is the emerging trends in science and technology. It is very much interesting. As already in the inaugural session of the seminar, already several of the respected colleagues have already talked about this. Actually, as time increases, you know, the emerging trends of the science is also increases time to time. So being a scholar, a scientific scholar, one should know what is the emerging trends in the various field of the science. If we talk about the science means everything like geology, botany, chemistry, physics, biotechnology, whatever the area includes in the science. So the theme of this conference is very much useful, and I hope that this conference will certainly be helpful for the participants who have participated in this particular conference. The title of today's talk is actually it is some of my research work which I have carried out in the last few years. So I would like to share some of the research work which I have published in last several years. So that the title of today's talk is the versatility of pipeline phosphate-based reagents in the synthesis of biologically potent scaffolds. Actually, my research area is already drug design, drug discovery. So in that theme, we are already engaged from several years in designing and discovering several kinds of biologically potent molecules. And while discovering the molecules, we used to discover the various kinds of synthetic methods, chemical methods. Some of the interesting methods on this particular talk, which I have already published in back years, I will be discussing about those methods. So the title of this, the particular focus on this particular talk is triaryl phosphine-based reagent. This triaryl phosphine-based reagent, some of the reagents I have used in the synthesis of some kind of biologically active molecules, which I will be discussing in this particular time. So the content of my talk is novel coagulation strategies implying Misnobu's reagent. And second one is novel synthetic methodology for the synthesis of alpha-aminonitriles implying Misnobu's reagent and triphenyl phosphine dibromide. So these are the different work which I will be covering. Now the question comes, what are the triphenyl phosphine reagent which I have utilized? That is, first one is Misnobu's reagent. Misnobu is a Japanese scientist who discovered this particular reagent for various kind of reactions. this reagent, actually the mixture of equivalent mixture of triphenyl phosphine and diethyl dicarboxylate, and the second reagent is triphenyl phosphine dibromide. With these two reagents, I have developed several kinds of chemistry, which I will be discussing in the forthcoming slides. So these are the various kind of molecules. These are the various kind of the molecules which we have synthesized in our lab using this trihalide phosphine reagent. That is 10 reagents. You see, here we have synthesized carbonates, we have synthesized dicarbonates, we have synthesized acetyl carbonates, we have synthesized carbonates, sulfates, alpha-glucanides, bases dicarbonates, dicarbonates, and carbonates. So these are some biologically potent molecules. Now, the traditional methods for the synthesis of carbonation reactions involve the use of carbon reagent like phosgene and its derivative, phosgene and carbon monoxide. So these are very much harmful reagents. And recently, yes, carbon dioxide and carbon disulfide has been used as a cheap and safe alternative for the synthesis of this kind of molecules. And in addition to this, carbon dioxide and carbon disulfide, we have used this triaryl phosphine based reagent. So we have used triaryl phosphine based reagent along with either carbon dioxide and carbon disulfide and various kind of starting materials. Now, the first compound we have synthesized that is carbamates. So carbamates is the stable class of the compound derived from the unstable carbonic acid by the substitution of amino and esterase through the various kind of alkyl halide derivatives. And second one is cyclic carbamate, where this 4-0-linkage is present in the cyclic system. Then this class of compound is known as cyclic carbamate. So carbamates we have synthesized. So this is all over the classification, whatever inorganic, organic, metal, non-metal, saturated, unsaturated, symmetrical, unsymmetrical, and in saturated we have aliphatic, aromatic, and others. So this is the overall classification of the carbamates. Now carbamates play an important role in medicinal chemistry and potential pharmaceuticals. Synthetic intermediates as synthons, as a protective groups called amino group, and also agrochemicals. So these are the various importance of the carbamates. And you see, there are many drugs which are bearing carbamates. First one is Texal. Texal is having this carbamate here. Next one is phosphostigmine, anti-Alzheimer drug bearing carbamate. And then third one is antibacterial drug, famous drug linezolid bearing cyclic carbamate. Fourth one is anti-HIV drug bearing propane carbamate, and fifth one is this carbaryl insecticide bearing this carbamate here. And also you see here, it has been realized by the scientists from the US that by removing this amide bond in the Texal to the carbamate increases manifold biological activities. So carbamates play an important role in medicinal chemistry. Carbamates generally, what I realized that by introducing carbamate into the biologically active molecule may lead to increased manifold biological activities. So that is why we have synthesized this kind of carbamates. So these are some other carbamate derivatives you see. Some of the natural products like discotamylide, metacin series. These are the natural products. And this is another compound, cyclohexyllectins, phosphostigmines. These are the various natural products bearing carbamates. These are some other compounds bearing carbamate linkage here. And you see all these compounds, they are so bearing the carbamate linkage. These are some other compounds bearing carbamate. This erythromycin derivatives, antibacterial drug, azithromycin derivatives. Hey, this linezolid and this hybrid molecules, bearing all these molecules bearing carbamates. So these are some other compounds bearing carbamate linkage here, like anti-malarial, antioxidant, anti-diabetic, anti-inflammatory, and anti-tubercular. So overall, I can say that carbamate plays an important role in increasing the biological activity of molecules. So that's why we have already cited some of the interesting molecules. These are some of the other molecules like carbamate. Here is anti-progesterone drug. This is anti-HIV drug, CNS active drug. All these compounds have a carbamate linkage, and here also anticoagulant drug bearing carbamate. Here anti-estrogenic drug bearing carbamate here. So these are the potential molecules. And beside the carbamate, we have also synthesized some dithiocarbamates. Now, what is dithiocarbamates? Like carbamates, dithiocarbamates are also the stable class of the compound derived from the unstable carbonic acid by the substitution of amino and sterines. So, when this linkage is present in an open system, then this is known as dithiocarbamates, and when this linkage is present in the cyclic system, then this is known as cyclic dithiocarbamates. So these are some of the importance of dithiocarbamates also. They are potential pharmaceuticals like drugs, products, and drug intermediates for the different kind of biological activities. They are being used as agrochemicals like pesticides, herbicides, fungicides, acaricides. They are used as intermediates for the synthesis of compounds, protection of amino groups and peptide synthesis, as an intersection control chemistry, as a radical precursor in free radical chemistry, synthesis of ion liquids. And then they are powerful ligand because sulfur is involved, so they are used as a powerful ligand for metal complexation. They are used in our industry for the metallization accelerator. They use transition metal complexes of the dithiocarbamates for used as organic superconductors. So this kind of molecules play many roles in the science. So these are some of the molecules you see here. Anti-malarial, this is anti-malarial drug. First one is bearing this dithiocarbamate linkage. Antibiotic drug bearing dithiocarbamate. Then another compound, anticholinergic drug bearing dithiocarbamate here. Antifungal drug bearing dithiocarbamate here. And then antimicrobial drug bearing two dithiocarbamates. So overall, dithiocarbamate is also very potential linkage and used frequently in medicinal chemistry. Now come to the chemistry part. Now, so we have used this particular. I already talked about two reagents. One is Mishnobu reagent, other one is triphenyl phosphondibromide. And while using Mishnobu reagent, we have synthesized a series of carbamates, phase, carbamates, acyl carbamates, substituted ureas, ACS dithiocarbamates. So using only one reagent, we have synthesized all these compounds. All these compounds using various kind of starting materials. So the first one now we are going in the detail how we have synthesized. The first reaction is the synthesis of carbamate. It's a very famous reaction. We have synthesized carbamates directly from various kind of primary, secondary, and tertiary alcohols using various kind of primary, secondary amines using Mishnobu reagent carbon dioxide system. And then, this is the mechanism of the formation of carbamate is, in first step, the amine is react with carbon dioxide from the unstable carbamic acid 1. And the Mishnobu triphenyl phosphate and dicarboxylate forms the Mishnobu 2. And when 1 and 2 react, it forms this ion 3. And 3 reacts with the alcohol, it undergoes rearrangement from the carbamate and triphenyl phosphate oxide. So the triphenyl phosphate oxide, this particular reaction is a byproduct. So this is another method for the synthesis of dithiocarbamates. Dithiocarbamates, which is Mishnobu reagent. Here we have used various kind of the primary alcohols, various kind of amines using Mishnobu reagent carbon disulfide system, which achieved in high yield dithiocarbamates. So this is another method for the synthesis of OS dithiocarbamate, OS dithiocarbonate, that's known as xanthate also. So various kind of the primary, secondary, tertiary alcohols, various kind of the alcohols used here, snowmurine carbon disulfide to generate various kind of xanthates. So this is another method for the synthesis of various kind of carbonates, various kind of the carbonate, various kind of the primary, secondary, and tertiary alcohols is using snowmurine carbon dioxide system. And from this particular method, we have synthesized various kind of organic carbonates here. So this is another method for the synthesis of thiocarbamates. Here, while synthesizing acyl thiocarbamates, we have used various kind of primary, secondary, and tertiary thiols, using various kind of the primary, secondary amines, using Misnomu reagent and carbon dioxide at room temperature. So we have synthesized here acyl thiocarbamates, very good yields. This is another synthesis of trithiocarbonates using Misnomu reagent carbon disulfide system. While synthesizing trithiocarbonate, we have used various kind of primary, secondary, and tertiary thiols. Later the Misnomu reagent. This is another synthesis of S-dialkyl dithiocarbonates using Misnomu reagent carbon dioxide system. So in this way, we have synthesized various kind of SS-dialkyl dithiocarbonates using various kind of primary, secondary, and tertiary thiols. This is another synthesis of carbonates. Carbonates are the carbamates of the hydrogens. Carbonates like carbamates are the carbamates of the hydrogen compounds, and the dithiocarbonates are the dithiocarbonates of the hydrogen. So keeping that same strategy, we have applied here, and we have used carbon dioxide reacts equal to oxygen or sulfur. When you use oxygen, there is carbon dioxide. When you use sulfur, there is carbon disulfide. So just summarize way, we have this particular slide, and in that way we have synthesized a series of these compounds using primary, secondary, and tertiary alcohols and substitute hydrogens using Misnomu reagent, carbon dioxide, and carbon disulfide.
Now this is another method for the synthesis of alpha aminonitriles using various kind of ketones, amines, and MSCN. Misnomu reagent at room temperature, high reactivity.
This class of compound used in synthesis of natural amino acids, and they are useful in synthesis of various heterocycles. They are displayed by range of potential biological activities. So these are the very important compound alpha amino nitriles. So we have synthesized using Misnomu reagent here. This is the overall mechanism for the formation of this alpha amino nitriles using TMSCN. This is another synthesis by the synthesis of alpha amino nitriles using triphosphate diaromide. Solvent-free acid with this kind of compounds, amines, MSCN. So this is all about the work picture. This is the mechanism for the formation of this alpha amino nitriles. This mechanism used to go to amine, the formation of amines. This triphenyl phosphine dibromide helps in the formation of amines, which subsequent reaction with TMSCN from alpha amino nitriles. This is all about the work, and thank you for your kind attention. If anybody have any question. इसको बंद कर दो।
Sir, since you are working on this kind of government since a very long time, so why not utilize this opportunity to tell? In I want to know that when we compare the carbon and biocarbon, which one might be the more beneficial for medicinal chemistry or biology? This is change of oxygen and sulfur. Thank you.
अब ये प्रथम टेक्निकल सेशन का समाप्ति हो चुका है और सभी लोगों की तरफ से डॉक्टर साहब को बहुत बहुत धन्यवाद कि उन्होंने बहुत ही प्रासंगिक विषय चुना, रेलिवेंट सब्जेक्ट चुना। अब बारी है लंच की, क्योंकि अब समय भी अभी हो चुका है और यहाँ लोगों का आग्रह है कि दो प्रधानाचार्य यहाँ आए हुए हैं, उनका स्वागत करते हुए हम लोग यहाँ से उत्तर बचते हैं। यदि कॉलेज मुरलीगंज के प्रधानाचार्य को सुमन जी मैथिली विभाग अगर उपस्थित हैं तो सुमन जी यहाँ हमारे कांग्रेस करें, आपके प्रकरणों से ही यदि कॉलेज मुरलीगंज के प्रधानाचार्य का स्वागत है। यदि
जी, बीएनएमबी कॉलेज मधेपुरा के प्रधानाचार्य डॉक्टर नवीन कुमार सिंह का स्वागत। डॉक्टर अखिलेश कुमार सिंह, बीएनएमबी के प्रधानाचार्य। अब यह सेशन हो चुका है और मैं सबों से आग्रह करता हूं कि अब हम लोग लंच
Prakash sir, are you able to hear us? We are audible to participants. Okay. Welcome to you all in today's second technical session. Our first speaker in today's second technical session is Professor Prakash Chandra Jha. Professor Prakash Chandra Jha is present and associated with the Central University of Gujarat. He is holding the multiple administrative responsibilities, an associate professor, teacher, and he is a research scientist. He is the Dean of Center of School of Applied Sciences, coordinator for university level industry academia in French, coordinator and nodal officer for Government of India, recently launched a flagship program, Bachelor in Vocational Study. Earlier, even he has served as the nodal officer of National Mission for Education through Information and Communication Technology. Before joining to Central University of Gujarat, he was associated in various capacities of Royal Institute of Technology, Stockholm, Sweden, Stockholm University, Jacobs University, Bremen, Germany, and the Center for Theoretical and Computational Chemistry, Tromsø, Norway. So I request Professor Prakash Chandra Jha, please unmute your mic and present your lecture.
Straight away,
Yeah.
I would like to request you, can you disable me for sharing my screen?
Yes, yes. I will make you a co-host, then you will be able to share your.
Yeah, please do that, sir.
Just wait a minute, sir.
Yeah.
Yeah, sir. Now you are a co-host. You can share your screen, sir.
Okay. Yeah, I hope I am audible to all of you.
Yeah, it's visible, sir.
Yeah, that's fine. So in this hot summer and after having a good lunch, to keep you awake is a really challenge for me. Knowing that, I'm going to give you an introduction of something which I don't know most of you might not be aware of. But before I move on to the topic about the introduction to the new branch of chemistry, which is now called computational chemistry, and from last 1 decade, it is making a wave across the world, not only in academia, it is more applicable today in industry rather than in academia. And in academia, in Western world as well as in United States, it is used quite frequently, which is very occasionally used and is still getting popularity in India. So straightway, let me thank the organizers who has dared to organize such a high-level conference from a degree college, MLT college, Saharsa. And I know this is not possible without the approval and the opinion of Honorable Vice Chancellor of the university. So I must congratulate and appreciate him. But he can give an idea. An idea has to be implemented by the group of army he has. And hence, the registrars, principals, deans, and all other colleagues who has been directly or indirectly helping them in making it successful. So I congratulate all of them, and I myself is very thankful to get a position, a time to talk to you, because I belong from Mithilanchal, and it's my privilege to serve my motherland. And my special thanks also goes to a vibrant and energetic faculty, Dr. Anand Mohan Jha, who has been running the scene behind. Now, after this, let me come back to computational chemistry. I don't know how many of you really know about computational chemistry, right? But we all certainly know about chemistry. And when we say we all know certainly about chemistry, chemistry is nothing but breaking and making of different kinds of bonds. That's it. And will it not be better that with open eye, if we are able to visualize breaking and making of the bonds? Will it not be better that the experimental tools can capture the movements of the atoms, bonds, dihedral angles? That means, will it not be better if we have tools to capture the photographs of a single molecule? Mind you, when I say single molecule, when you go to the experimental lab and you try to synthesize the molecule, it's hardly the case you are synthesizing a molecule. Rather, you are synthesizing Avogadro molecules. So what I'm trying to show you in the left-hand side, that the molecule is dancing and the dance is captured by the recently developed experimental tools, and which can be checked by what is called computational chemistry on real life time. What I am showing you in the right-hand side is in the given molecule, how does a one particular bond breaks and how does one particular bond is made. That is two sides. In between, you will see it's written next big hit in molecule Hollywood world is capturing the motion of single molecule. Now, this leads me immediately to a question whether computational chemistry and experimental chemistry can go together. Is it in synergy or is it in contrast and comparison, contrast and compare to each other? It is always good to that when we have two, we are better than one. And so basically, there are many incidences you will encounter, and in fact, people have encountered from several hundred years. There are many incidences where you observe something experimentally and you find it very difficult to prove or disprove. Even modern times too, when you synthesize a new compounds, you are not 100% sure what can be the mechanism of that formation. So what do? You try to put the plausible mechanism. which has yet to be verified. Like this, there are many incidences, many different kinds of situations you encounter where experimentally it is very difficult to give the reason behind the origin of those kind of situations. And there comes what is called a computational chemistry, a toolbox of a chemist. It's a nut and bolt of a chemist based on mathematical foundations and computer science. So basically, in one line, when I use the word computational chemistry, the message is very loud and clear that we are talking about experiments on computer instead of in the chemical lab. Okay? That brings me to the point, if we are already in the virtue of entering into 21st century. In 21st century, people are always talking about sustainable energy, sustainable life. There are many problems across globes, and the future leads to be difficult. In that situation, as a researcher in the domain of chemistry, if we try to understand ourselves, that can we sustain the kind of chemistry we have been doing 10, 20 years before in coming 10 to 20 years? The answer is no. It's next to impossible. So if the chemistry has to still survive, then we need to find a way where we need to have inventing sustainable future, right? So we need to move from multidimensional, multidisciplinary, interdisciplinary, transdisciplinary. Means the domain of the disciplines is more or less is disciplinary. So if you want chemistry to help us in inventing sustainable future, then it must have at least most important triple rule. The role number one is creating new scientific knowledge, translating why you are creating knowledge. What is the use of creating knowledge? Because we need to translate that knowledge into useful applications. And when you talk about transferring this knowledge to useful applications, then basically we are trying to helping to meet the emergent challenges of multiple unfolding global crises. Okay? That means we are doing science to find out the answer of those questions which is raised of different level of different kinds. And we need to find out the answer, right? See, many of you know that in periodic table now you have 112 elements, you know. But according to me, it should be 113 elements. And 13th element has to be SU. SU in the sense, sustainable element, okay? And there is a beautiful book which has come in the market, which is called Chemical Element, which is Sustainable Elements in the periodic table. So this is trying to tell you, chemistry is not about doing science in the laboratory, but improving the lifestyle of the human being. That means if you sit down and think yourself from the time we go to sleep on the bed and from the time we get up, where chemistry is not involved. Everywhere there is a chemistry. Only thing we do mistakes, either we ignore it or we don't understand. That means if we try to answer any question in real life related to human life, then the chemistry boils down to what is called vanity. Question can be about vanity, vitality, virility. Okay? So if we have an ambitious goal of going to the moon, okay, then we certainly need to undergo major changes in our priorities, approaches, and practices. And that can be done until unless the practice and teaching of chemistry is not done with its external orientations. That means the connection and engagement with other disciplines are also important, with goals and approaches of one world of chemistry. See, from class 11th, we have been taught the new branch of chemistry has been introduced, which is called organic chemistry. But now you have a chemistry which is called computational chemistry, and it's a silent about any elements. That means it is applicable equally well for physical, inorganic, organic, organometallic, polymers, proteins, DNAs, RNAs, and so on and so forth. That means the message is very loud and clear. Now, this is a branch of chemistry. The concept of this chemistry can be applied in any branch of chemistry. So it encompasses all the branch of chemistry, right? Well, if you have not heard of it, or if you have heard of it, in both the cases, if you are thinking of, if you have heard of it, thinking of future in computational chemistry, then I must tell you that your life is certainly very secure and it is in the safe hands. Why? Because in the left-hand side, if you look at this, it's poster says, this is a poster from a Hollywood movie, which says, better living through chemistry, right? And the right-hand side, I write models of success, okay? But how they can be models? They are three very old people, right? On the left-hand side, they are like young boys and girls, and they are graduate students. And I must tell you, all the boys and girls who has acted in this Hollywood movie was a science graduate. That also tells you that as a science graduate, you qualify to be movie star also. And at the right-hand side, the model of your dream. That means if you want to have a life in science, that means you dream of Nobel Prize. So all on the right-hand side, these three gentlemen has been awarded recently Nobel Prize in Chemistry for their computation and the foundation of computational chemistry. Right. Now, leaving everything besides, coming back to the science, if you look at that, what I am showing in your next slides, this present slides is, on the y-axis, I have plotted time. On the x-axis, I have plotted length. In between, I have written methods. Through this, I am trying to convey two messages. One, whether you are dealing with proteins, vitamins, or molecules, atoms, polymers, or anything else, that means size doesn't matter. You sit down and think yourself, what are the difference between atom, molecule, polymer, DNA, protein? The only thing changes is size. And that leads to change in the properties, which happens at different time scales. And time scales could be from femtoseconds to years. If you remember, Ahmed Jewell around 2012 has been awarded a Nobel Prize for what is called femtosecond spectroscopy, right? So that means he has first time devised the way to capture the experimental phenomenon which happens at femtosecond level, okay? So exactly, depending on the kind of the system you deal with, you have a different approaches to solve it. And that is quantum mechanics, molecular mechanics, and all those methods are available. And as the experiments have its own limitations, computational chemistry has also its own applications about the area and the kind of problem it is dealing with. Okay, so in one sentence, if I want to say anything about any kind of problem, whether you are a physics graduate, chemistry graduate, or a life science graduate, what you're dealing with. If you're a chemistry graduate, you are dealing with molecules. If you are a life science graduate, you are talking about protein folding, proton transfer, and ribosomes. If you are from material science, we're talking about biomimetic compounds, polymers. So what I am trying to show you by these slides is very, very simple. Kind of system you deal with, the length and the time scales involved are very different. So for each different domain, you have a different computational methods to answer the questions which is raised in those domains. Okay, that part has to be done, and those methods are known. And those methods are called classical simulations, QMMM, first principle simulations, and so on and so forth, right? Well, computational chemistry is not your wish, whether you want to know or you don't want to. You know that in the world, there are two famous chemical societies. One, American Chemical Society, another, Royal Society of Chemistry. The recent president of Royal Society says, and he predicts, that after 15 years, there will be no chemist who will go to do the bench experiments without doing computer modeling. So he's indicating if the computer power is increasing and it be becoming easier to buy, why not check it, get the preliminary results before we go to do the bench work. This in turn is indicating you will save time, hit and trial, optimizing the conditions, and you will save chemicals, manpower, and so on and so forth. Okay, so that was his predictions. Okay, and that is coming true. Now, this is taking me to the point where whether you talk about, this is specifically, I will be talking today only about computational chemistry, but if you're talking about computational chemistry, computational physics, computational biology, then we should really understand what is computational chemistry, right? That is the first question that comes to your mind. Second question, which might be disturbing you, is what kind of problems we can solve with this, okay? And to solve that kind of problem, what kind of tools we use, and so on and so forth, right? If you want to answer these questions, then the first and foremost important thing is what is not covered in computational chemistry. Whether you are talking about microscopic world, to nanotechnology, to daily life, to environmental problems, from life science to human disease to drug design. What is the difference between all of this? As a chemist, we try to think everything is made of atoms. And these different branches are divided only by our minds. This is one part, that what is not covered. Then you ask yourself, what cannot computational chemistry deal with? Sit down as a chemist and think. In any branch of chemistry, what do? You do only three things: reactivities, energetics, structures. Only three things you do. And you use different kind of experimental techniques to reach on some conclusion on that. For example, if you're talking about spectroscopic techniques, UV, IR, Raman, NMR, VCD, and so on and so forth. So basically, a structure to property or the reactivity you are talking about. So modern days computational chemistry has reached to the point where whatever experiment you do in the wet lab, you can do in silico also. Okay. Of course, it is easier said than done, because the kind of system you deal with, that kind of supercomputer you need. So it's not that you have a desktop computer and you wish to solve 50 atom problem. It is easy. No, it's not. But if you compare today's situation with 15 years before, it has become easily affordable and easily doable. Just an example I'll give you on a lighter side of it. One fine day, one student who asked to science, Dr. Science, that I hear that scientists have made anti-hydrogen. And then the question is, if you mix the anti-hydrogen with anti-oxygen, could you make anti-water? So this is a level of imagination up to which you can use computational chemistry. Anyway, now, if you're talking about modern days computational chemistry, the genesis and the origin goes to 1933 in the Nobel lecture given by one of the founding fathers of the quantum mechanics, who said very clearly during his Nobel lecture, remember, we are talking about 1933, when there was nothing called computer, okay? But at that time, he could imagine that something like that is about to come, or there is no way out. And then he proposed that the underlying physical law necessary for the mathematical theory of a large part of physics and whole of the chemistry are completely known. He said at the time, everything or anything you want to know for chemical system, mathematically it is known. But the problem is, mathematical equations derived on the basis of basic principles of chemistry are too difficult to solve. Means human power cannot solve. After the advent of computers, slowly and certainly that has become visible. So if you look at 30, 40 years before, that science was standing on two legs. You know, if you look at the triangles, it is stable only when it has vertices and the two legs. So earlier it was theory and experiments. But the mixing link between theory and experiments, which is called computation, was missing. So after the advent of computers, that has come and that become possible. Okay? So that is what is computational chemistry is. So if anybody asks you, what is computational chemistry? You will say science with computer instead of laboratory. And you can use these computer calculations to predict the structure, reactivity, any kind of properties, okay? And in recent times, this has become widely used because of the dramatic increase in computer speed and design of efficient quantum chemical algorithm, okay? What are the advantages? Advantages are very simple. It enables us to explain and rationalize the known science. Because if somebody asks you, what is the proof what you have calculated or what you have predicted is right? Then the answer is very simple. Whatever is known, proved, if my mathematics can prove that, then why not using same mathematics I can predict what could happen? That means it is giving you the way not only to answer or rationalize the known science, but also giving you the way to answer unknown science too, okay? Many times it helps you in interpreting experiments. So if both goes together, it's good enough. And basic standard of understanding of science will increase. So I will not take much time because we are already running late. I will just take 5 to 7 minutes more by giving you one or two simple examples of daily life where how computation it has changed the world, the way we think about science. Okay, and I will start with a very simple and interesting examples. For chemists, it's a bread and butter. It's a ruthenium complex. And what do you do in the ruthenium complex? You synthesize, you get the crystal structure. Getting the crystal structure means getting bond length, bond angle, dihedral angle, right? And then you report, and then you are happy, and you look for the properties, and so on and so forth. Now, I'm showing you well-known ruthenium complex. I have just compared, if you look at the screen carefully on the right-hand side, bottom one, the last two columns are computed in experiments, okay? If nobody tells you which one is computed in experiments, it is very difficult to predict which one is what. That means the computation has come to the point where it can challenge the experiments and vice versa. That means wherever the experiment is not possible or difficult to do, even you can do theoretical predictions, which can be better than nothing. Okay, and most often than not, it will be more closer to the experiments, and that's good enough. Similarly, I'm showing you another thing. The same ruthenium complex, if I am interested in getting very simple examples I'm giving you, just to give you the flavor, that if you want to predict some kind of a spectra, absorption spectra in different solvents, you can see the difference between experimental observations and the theoretical one is not very far. So the trends are right. That is important rather than exact numbers. But the most important part than that, when you see the spectra, then you say LUMO, HOMO, LUMO -1 is involved. But the question is, which one orbitals are contributing in making those LUMOs and HOMOs? So if you look at this picture, it certainly tells you how does the electron density is shifting from which orbital to which orbital. So it is telling you about the charge transfer characters. So these things you can easily look with your open eye with the help of computational chemistry on the computer screen. Okay. I will not take much time as I promised. I give you another example. If you all remember, then around 2010, when the Sony has launched first time OLED, okay, TV, then it used to be for 22-inch, it used to be more than a lakhs, 1.5, 1.4 lakhs. Okay. Okay. And the problem, even in buying the TV, 1.5 lakh is not the problem for many people. But the problem was there is a lifespan which was very, very less. So when you go to buy, you ask how many years minimum guarantee and warranty. They will say 2 years guarantee and maximum warranty will be 6 years, 5 years, 7 years, and so. So the question was how to get rid of this estimated lifespan shorter than expected. If you are investing in 2010, not 2022, 1.5 lakhs, you expect it at least to run for 10 years, not for 5 years. So then scientific people sat together and found what is the problem which is leading it to the shorter lifespan. Okay. Then they sat down and analyzed the materials they used for making it, and they tried to look into characterize it. And when you look into that experiments fully, then you will see they use the polymers and organic polymers. And what kind of experiment they did to characterize those polymers? time resolved photoluminescence, excited state absorption spectroscopy, fluorescence, phosphorescence, flash photolysis, chiro-optical absorption, emissions, UV, IR, and Raman. The challenge is how many different kinds of polymers and what is the criteria of selecting those problems, selecting those polymers to solve the problems of estimated lifetime so small. That was question number 1. Question number 2, it was expensive. Question number 3, all these characteristics and technique was taking time. Question number 4, manpower. At the time, in 2010, some of the Japanese scientists and the Sony, I was in Stockholm at the time, working part-time with a Sony Ericsson company, and they came with a proposal, and we did try to scan all these properties, and we tried to find out and propose some of those molecules. So what we suggested was, you get me a series of polymer which you want to synthesize, and I will get you all these properties, and then you decide which one to move for. In 2010, okay, and so on and so forth. That we did. Similarly, there was another problem, which is very simple problem of sensitization of cancer cells to the light. If you look at this picture carefully, what I'm showing you is very simple. Surgeon's hand in operation theater room, what he's trying to do, he is passing a beam of light which is traveling along fiber optic cable for photodynamic therapy. What does that do? So the patients will be given such kind of dose, photosensitizers, before operation 24 to 48 hours. Okay, and you will see that process is called cancer photodynamic therapy, and that kills the tumor cell. But the problem with those kind of mechanism is that it is based on what is called one photon absorption. Okay, and if you use that kind of technology and that kind of phenomenon, that automatically the limitation is it has a high absorption at longer wavelength, high singlet oxygen quantum yield, low photobleaching, high chemical stability, low dark toxicity. And how to get rid of that? And in fact, with the help of Canadian group, we proposed the molecule which is shown in the right-hand side. And in fact, this boils down to a simple chemistry lab Jablonski diagram. And as you look at this figure, I'm not showing anything else. I'm just trying to show what happens if you shine the light on a particular kind of materials. If it is in singlet, it will go to excited state, singlet, first excited state, second excited state, singlet. What is the option it has? After that, it can do intersystem crossing to come to triplet. And then it has another option. Either this triplet can come to the ground state, or it can go to the higher triplet state. And later on, we did find out that solving this problem is optimizing the material for lesser intersystem crossing, and so on and so forth. I am running short, but I must tell you that we did try to show and propose what kind of material that can replace this kind of existing drugs, okay, and so on and so forth. Last but not the least, every time medicinal chemist talks about, most of the times, and in fact, around 25% of all pharmaceutical drugs contains an amide unit. But even today, knowing that 25% of all pharmaceutical drugs contains an amide unit, even industrialists ask to the academicians, do you have methods of efficient imidation? Okay. Or if they ask the question, is there any methods to access amides directly from carboxylic seeds and more? If you look into the literature carefully, and if you try to find out what is known and what is not known, you will find, yes, there is a method, but it has a problem. And the problems are very, very simple. The methods are that the byproducts are large and the reaction takes place at 160 degrees C, which is not favorable. So one of the pharmaceutical giants came with these proposals, and we tried to optimize the reaction conditions, including the reagent, and we showed that how much yield by which part you will. By giving you these kind of examples, I just wanted to leave a flavor for you to know the computational chemistry can be applied across different disciplines and certainly across different branches of chemistry. If you have any questions, query, you can always come back to me. My email ID has been with organizers, and I will be more than happy to answer any question, query you have. These works are not possible without the help of my PhD students and some of them who has graduated and now they are positions in some of the best institute in the country. So, and I am thankful to many collaborators across the world. Thank you very much for kind concern and listening. Thank you.
Okay. Thank you very much, sir.
Yeah.
If any participants have any doubt, okay. If not, let me thank Professor Prakash Chandra, sir. Thank you very much, sir.
Thank you.
On the behalf of organizing committee and MLT College Saharsa, I thank you very much for delivering a wonderful lecture here. Now we will move to our next speaker. Hello. Dear participants, now we will move forward, and our next speaker is Professor N. Arul Murugan sir. He is currently Associate Professor at Department of Theoretical Chemistry and Biology, School of Chemistry, Biotechnology and Health, Royal Institute of Technology, Stockholm, Sweden. He had a docent degree in 2015 and appointed as a docent in theoretical chemistry and biology at KTF, Sweden. He did his PhD in 2005 in computational chemistry from IISc Bangalore. He has a long research and teaching experience. He has more than 100 articles published in the reputed journals. He is teaching the courses like molecular modeling, physical biochemistry, biomolecular structure and function, drug development. So with these words, now I will invite Professor Arul Murugan sir to deliver a lecture. Yeah, your screen is visible, sir.
Yeah, are you able to hear me now? You are able to hear me, right? Hello?
Yeah, it's visible, sir. Yeah, we can see the field.
Okay. So, should I start now? Okay, hello. If you are able to hear me, I will start. Let me once check whether you are able to hear me. Okay, my mic is on. I hope you are able to hear me. Can someone say yes or no?
Sir, you are audible and your slides are also visible. You can start your presentation.
Okay, thank you very much. Yeah. So first of all, I thank the organizer for giving me an opportunity to present about my research related to drugability prediction using different approaches, and it is, I think, something very similar to what Professor Jha presented some time ago. So he was talking about the computational approaches for materials modeling, right? So what I'm going to focus is that how to use the computational approaches for drug like, or drugs development or tracer development. Okay, and then one different, I'm going to focus on only the neurodegenerative diseases. So you are going to learn what these are, and then how to use computational approaches for drugability prediction. Okay, so independent of whether they are tracers or whether they are drugs, they need to fulfill certain properties, which is called, which is measured in terms of druggability of the compound. So I'm going to talk about how to, predict these properties using computational approaches, because you can use experimental techniques like high throughput screening, like target discovery. So you can use different experimental approaches, but the problem is that they are one thing is like they are time consuming, and then they are like they demand a lot of resources, and they are like destructive. That means you spend a lot of chemicals, manpower. So that is the reason we want to use the computational approaches. Like at least the idea is that that the chemical space has 10 power 60 compounds, right? Or you take zinc database, it has like billions of compounds. So we cannot use experimental techniques to screen, using all these compounds, because it's going to be consuming a lot of resources, time, manpower, So that is the reason we want to use the computational approaches. So the idea is that you narrow down the chemical space that you want to screen using some computational approaches. So from billions, you bring them down to like 100 compounds. Then you can use the computational experimental approaches to validate, out of these 100 compounds, which are the best drug-like compounds or tracer-like compounds. Okay, so that way, you have cut down the, so much of demand for resources, time, and all these things. That is the thing I'm going to focus on, like how to use the computational approaches to predict the druggability. That's what I'm going to talk about. So actually, recently I moved to IIIT Delhi. I was working at KTH until 2021 December, and then now I moved to Indraprastha Institute of Information Technology. So so if you want to reach me, just check our institute homepage, and then you will find me. Okay, so I will just quickly give what are the neurodegenerative diseases. And how to use the computational approaches to develop therapeutics or diagnostics. I will show some applications in the end. I think my talk was was assigned for like 30 minutes. I will try to stick to time, and then I'll wind up in time, so should not be a problem. So the we know that cancer is very it's like killing a lot of people in India, all over the world. So there is also another most dangerous disease. I will say that they are the neurodegenerative diseases. They used to be the like concern for the people from developing countries like Sweden, many years ago. But now it's not anymore. Even in India, we have so many people getting affected by neurodegenerative diseases. Our own relatives, being diagnosed with Alzheimer's disease or Parkinson disease, so these diseases come under the category called neurodegenerative diseases. So what happens is that the people, they lose the motor abilities or speaking ability, or they develop dementia. They forget things. So it even becomes that they forget their own dearest relatives. So they completely lose the memory, and after a while the disease become lethal, and people even pass away. So it is really a dangerous disease. So they really slowly lose the memory, and then at the end they become no more. Okay. So the cause has been attributed to the accumulation of certain proteins in brain, intraneuronal or extraneuronal compartments, and basically these proteins are they have functional form. They are supposed to do some activities, like they have to supposed to metabolize neurotransmitters. They are supposed to break down certain proteins, but then in certain conditions, they tend to create a form, which is like tend to aggregate, in larger and larger size. So they form aggregates, then they form fibrils, then they form fibrils. So then, actually we have the body mechanism to repair, if there are some fibrils formed, so we have body machineries to remove them out. But then when it happens at a accelerated rate, then the body machineries cannot do anything. Then basically, it takes to the pathological state, which is anymore not reversible. Okay. So then people, there is no signal transduction from between the neurons. So people start generating dementia and all those things. So these are various neurodegenerative diseases, like I have listed them, like Alzheimer's, Parkinson's, chronic traumatic encephalopathy, and progressive supranuclear palsy. So there are so many neurodegenerative diseases, and if you see in the right side, I'm connecting it to the specific fibril, which contribute to this disease. So in case of Alzheimer's disease, it is rather tau fibril and amyloid fibril which are accumulating in the brain. And if you take Parkinson's, it's rather alpha-synuclein fibril which is causing the disease. So idea is that there are different therapeutic routes. One way is like you can develop molecules which can bust the fibrils. Then basically once they are become insoluble, then we have the body machineries to remove them away. Okay, so these compounds which can bust the fibrils, we can develop computationally. Okay, the other approach is that you develop inhibitors which will act on the enzymes that are responsible for the production of amyloid forming peptides. So the beta secretase 1 kinases, they are belonging to such a category. Okay, so you can rather develop some inhibitors for these targets, and then they can contribute to therapy. Okay, so the third option is that you can also develop inhibitors for various enzymes which are metabolizing the neurotransmitters like monoamine oxidase V, acetylcholinesterase, beta-cholinesterase. So this is the third route where how you can develop therapeutic compounds for the diseases. And when it comes to diagnostics, of course, there are like PET tracers and or optical markers which can measure the fibrils accumulation in the brain or in sample. So that is for developing diagnostic compounds. Okay. So let me quickly explain like how we do medical diagnosis and what is the mechanism behind that. So basically, in the normal condition, there are certain genes which are expressed, and then the disease condition, there are different sets of genes are expressed. Okay, so there are compounds which can specifically bind to these enzymes, and then they can show their population. So then by measuring the population, we can find out whether a specific disease is there or not. Okay, for example, you take cancer, the cyclooxygenase 2 is expressed in larger quantity, then telomerase is expressed in larger quantity. In case of Alzheimer's, we have like translocator protein or monoamine oxidase B, amyloid or tau fibrils. So there are certain compounds which you can use to measure the population, population of these enzymes, okay, or fibrils. I'm just giving you. I want to be more like in the sense I don't want to give it like a research presentation, but rather I want to do it like like teaching, so where since there are many undergraduate, postgraduate students, I want to do it this way. Okay, I didn't make it like a research lecture, but rather like course material. Okay, so I think you will find it useful for you. So there are compounds like thioflavin T, so you like it can be used to measure the the aggregation rate, also the the state of aggregation, and then the amount of aggregates formed. So you can use the THD as a compound. So the fluorescence intensity of the THD is proportional to the amount of fibrils in the given sample. Okay. In addition to that, there is also shift in the spectra. It shifts to, it shows the red shift when there is fibril in the given sample. Okay. So by measuring either the shift in the spectra or by measuring the fluorescence intensity, you can find out, you can correlate it to the presence of fibrils in the given sample. So that is coming under the category of in vitro imaging of fibrils. But then one can also do in vivo imaging. Okay. So let us say, in a living subject, there is accumulation of fibrils in the brain or other organs. Then, you cannot take away the sample, let us say, then in this case, how you will do? So there is another way that you inject these Pittsburgh compounds, then it goes into the organ and then it binds to the specific target. Then when you are doing the PET imaging, then you will see that there is, signal which is proportional to the amount of fibril in the organ. So you can see that using Pittsburgh compounds PET imaging, you can distinguish the normal patient from the patient with Alzheimer's disease. Okay, so the right side image corresponds to control normal patient, and then left side one corresponds to the patient with Alzheimer's disease. Okay. So even though this disease is like more than 110 years old, so far we don't have any therapeutic drugs, and there are some drugs reported, but then they only treat the symptoms. Okay, that means like they can only affect how the neurotransmitters are metabolized, but the cause of the disease is not altered at all. So still there will be production of amyloid fibrils in the brain. So only thing is the disease, the condition is a little bit delayed, but then still the disease will take away the human. Okay, so it is the pathetic situation of the therapeutics and the diagnostic concerning the Alzheimer disease or any neurodegenerative disease. So there is a lot to be done. Like we have seen a lot of development when it comes to cancer, but it is unfortunate that we don't have made so much big development in terms of diagnostic therapeutics development for neurodegenerative diseases. So we really need lot research to be done to come up with useful compounds. But the drugs design is not that easy topic. The problem is that a drug discovery is a multivariable optimization problem, where you have to simultaneously optimize many properties. So all these properties come under the category called druggability. So like binding affinity, binding specificity, pharmacokinetic properties, pharmacodynamic properties. So all these property we need to optimize. Since it is a multivariable optimization problem, it is challenging. Okay. So another thing is like coming to PET imaging. We have PET imaging of brain. There are a lot of challenges. One thing is like in brain there are so many biomolecules coexist. So then the compound should specifically go and bind to the target that we are interested in. But this doesn't happen always. For example, there are like tau tracers which bind to amyloid fibril. So the tau tracers, they are supposed to bind to the lowermost bottom right side tau fibril. I show you here. So they are supposed to bind to it, but the problem is they may also bind to the amyloid fibril. Same way, the compounds which are supposed to bind to amyloid fibrils, they also bind to some extent to tau fibril. So basically, then there are tau tracers which are supposed to bind to tau fibril, but then they also bind to the monoaminoxidase B. I will little bit come to that. But the problem is, as you can see, that the compounds are not specifically binding. That means even though they have the binding affinity, but then they have poor binding specificity. So this leads to the misdiagnosis. Like for example, we are supposed to measure the population of amyloid fibril, but then since these compounds bind to other targets, then the population is not the right one. Okay, so because the signal is not directly proportional to the population. So these type of issues are there. And in addition to that, the fibrils, you take all the fibrils like amylin fibril or synuclein or fibrils formed from lysozyme, insulin, tau protein, all of them have the rich beta acid structures. So they are rich in beta acid content. So the compounds will find it difficult because usually they are like hydrophobic surfaces, and they are in all such fibrils. So the compounds may find it difficult to specifically bind to these fibrils. So you develop a compound for the amyloid fibril, then there is a high chance that it also binds to tau fibril. Okay, so these type of issues are there. So that's the reason we need to really improve the binding specificity along with the binding binding affinity. Okay, so now let me say that a few words about how we can use computational approaches. So the computational approaches can be used from bottom to end. Okay, just before the clinical trial, you can come up with the lead compounds using the computational approaches. Like you can do target discovery. Once you know the targets, then you know the sequence. Then from that you can use homology modeling or de novo 3D structure prediction approach. Then develop you can propose 3D structure for the protein. Then once you have the protein structure, you can do structure based screening, which is called virtual screening. Then or you can go for a de novo design, because once you know the microenvironment in the binding site, you can always find the compounds which will bind very strongly to that target. So this is called de novo design. Like you can build it by atom or by fragment. But you can design new molecules, entirely new molecules based on the microenvironment. So that's possible computationally. Then in addition to that, you can also predict ADMET properties, side effect modeling you can do. So the advantage is that it's like the computation approaches are less expensive, less time taking, and you can automate them. You don't need so many human resources. You can write some script, and then you can run it in parallel over like 1,000 core, 10,000 cores, and then you can complete the screening very fast. So this is quite possible, but then only issue is that the accuracy, right? So they have there are different methods like force field methods, quantum mechanics based methods, machine learning based methods, and then the accuracy varies in these different methods. Okay, so when you wanted to predict the druggability, then these property need to be computed, right? Then only you can use the computers to optimize this property. So now I'm going to talk about how to compute this various druggability. So which is the property of relevance. So there comes the free energy of the ligand, which is the relevant property, using which you can compute any of the drug-like property. So I'm trying to show you that the binding affinity is nothing but it is a free energy difference of the ligand in target-like environment to water-like environment. Same way permeability, you can say that it is a free energy difference of the ligand in membrane-like environment to water-like environment. Same way like solubility, water-like environment to crystal-like environment. So you can measure the or compute the druggability using as a measure of free energy differences. Okay, so it's quite possible. But the only problem is, even though we can relate this to some computable property, but the problem is how reliably we can compute is a big problem. So there are like we need this accuracy of few kilocalories per mole in order to rank the compounds in the right way, so that the results we obtained are reliable. Okay, so so that you can take directly to the clinical trial or phase 1 trial. Okay, so but then so the challenge here is that how accurately we can compute this drug-like property. Okay, so that is the challenge here. So there are so many approaches for, let us say, binding affinity is one of the druggability property, right? So how to calculate it? You can use different approaches like docking, MD plus MMGBSA or QMM based approaches. So the accuracy increases from left to right, but then the computational expense also increases from left to right. And then the number of compounds you can screen using such approaches decreases from left to right. Okay, so these are certain limitations, like like certain accurate approaches, they may take time, but then the good thing is like they are very accurate. Okay, so now let me show some results like using the computational methods, how to make sense out of the experimental data available on binding profile of different traces. Okay, used in Alzheimer's diagnostics or imaging. Okay, so as I said, like there is a control, and then you have different type of the intensity or positron signal coming from there. When it is AD, then you have different type of signal. So from the signal, you can, or from the PET scan, you can find out like whether a person has disease or not. So here we have been trying to use the molecular docking, MD, MMGBC approach to understand like the how to explain the binding profile. So there are many experimental data available on how the amyloid tracers bind to amyloid fibrils 1 to 42 and 1 to 40. Okay, so the results are like that. You can see that the binding profiles so that the compounds, certain compounds, they bind to a specific binding site. And one thing is there are multiple binding sites, and some compounds specifically bind to a single binding site. Some compounds bind to one binding site with a larger extent, and then to another site with a less extent. So the preference for different sites is different for different tracers. So these are the available experimental data. So we try to understand using the computational methods. As you can see here, like there are tracers which bind to the amyloid fibril with nanomolar binding affinity, and then there are there are other sites where the tracers bind with submicromolar submicromolar binding affinity. Okay, so the binding affinities are different for different binding sites. So we have been trying to understand that using the computational methods. Then the next thing is related to tau imaging. Also, there are a lot of data available. So what they show is that at least there are 3 different binding sites for the tracers in tau fibrils, and then some compounds bind to all binding sites, with comparable binding affinity, and some compounds they specifically target single binding site. So these are the available experimental data, from tau imaging agent study. Okay. Or so then through our modeling we wanted to explain, and we did like docking, molecular dynamics, free energy calculations, and we could show that there are of course the multiple binding sites for the tracers in amyloid fibril 1 to 40 and 1 to 42. In addition to that, we showed that the core binding site is the most high affinity binding site, because that was able to like nicely reproduce the experimental binding affinity profile for various tracers. So we proposed that it is the core site which is responsible for high affinity binding in case of amyloid fibrils. Okay. So in case of tau fibrils, we also could show that there are at least 4 different binding sites, and some compound like PBB3, they can bind to all sites with comparable binding affinity. But then let us take MK6240 or T807, they only specifically target single site. The binding site 1, they only target with high binding affinity. So we were able to explain all the available experimental data, and we also could show that why certain tracers bind with high binding affinity and others with low binding affinity. So such useful information we were able to get, and here I'm showing that how to use computational approach to model the specificity. Like this compound CQ, which is is known to bind to amyloid fibril with high binding affinity, but then to other fibrils you can see from this the fluorescence intensity data of this compound in different fibril environment. You can see that it only binds to the amyloid fibril with high binding affinity, but not with others, like whether let it be like alpha synuclein fibril or tau fibril, or even alpha amyloid fibril monomer also, sorry, amyloid beta monomer also it doesn't bind. So we want to explain like what is the reason. So we did the modeling, and then we could show that only when it binds to amyloid beta, the binding affinities are in the in the range -14 to 28 kilocalories per mole. That means they have much higher binding affinity for amyloid beta than other fibrils, because in other cases the binding affinity range was only in like few kilocalories per mole. Okay. So we could explain that with the modeling, that why certain compounds have specificity for the different amyloid fibrils. And here I show you one example, like how to model the off-target binding of the tracers. Okay, so I'm just taking the example from monomonadase V. So there were experiments done on these tau tracers in brain. So what they found was that when they did experiments with the THK5351 tracer, they could observe the signals coming from the basal ganglia and thalamus, where usually the monomonadase B is expressed. Okay, so they are supposed to bind to tau tracers, but then the signals are coming from the region where MUOB is expressed. Okay, so then the people were suspecting that maybe this compound, in addition to binding to tau tracer, maybe it is also binding to monomonadase B. So then we conducted some modeling studies. So we took all tau tracers and then we studied their interaction with the monomonadase B. So what you found was that most of the first generation tau tracers, they in fact bound to the monomonadase B very strongly, with the binding affinity comparable to that of the safenamide, which is a known MAOB inhibitor. But then the interesting news is that we also could predict that second generation tau tracer like JNJ311 or pyramidal compound, they seem to be binding to MAOB with least binding affinity. So we propose that maybe these compounds, the new second generation tau tracers, are the best compounds for the tau imaging, because they have the least off-target binding to MAOB. So in fact, this pyramidal compound is under clinical trial, and then they are proposing it to be the best compound for the tau imaging. So the interesting thing is that with the modeling, we could show that which are the tau tracers having the off-target binding to MAOB, and then we can even identify the best tau tracers for tau imaging. So that type of information we can get from modeling. Then let me go further. Even you can design new compounds for the tau or amyloid fibrils. We have some results there, but this need to be validated anyway. But then now let me go into the next topic. That is like the force field approaches are fine when you want to screen bigger chemical spaces, but then you want to rank some compounds with high chemical accuracy, then there is a problem. They are not doing very well. That means that they are not able to explain the mutual polarization between the protein ligand subsystems. So rather the more reliable theory is the quantum mechanics there. Okay, but then quantum mechanics theory is suitable for studying only systems of very smaller size, let us say like 100 to or less than 200 atoms, because the cost goes like n power 3 to n power 7, where n is the one electron wave function. Okay, so you think about some atoms of size more than 200, you will see that the computational resources we have, they are not really enough, and then the computation demand explodes. Okay, so then how then if we cannot approach the if but then how do we use the quantum mechanics to study the protein ligand interactions? So there are there are some different approximate approaches, like QM crystal model or QM fragmentation energies, QM fragmentation method or QMMM method. So we can use quantum mechanics to study protein ligand interactions, even though the protein ligand system is having size of like 2000 or 5000 atoms or something. Okay, so I'm going to little bit show some results from there. So we have done our own implementation of this fragmentation scheme. So what you do is you take the protein ligand complex system, and then you fragment the protein into individual amino acids. Then you conjugate, you cap them with some groups like hydrogens or some groups, and then now you estimate the energy of the interaction between the fragment and the ligand. Then you do this for all fragments. Then you sum this over for all pairs. Then you get the total interaction energy. So, but one thing is that since you have added this conjugate caps, you have to remove the interaction energy added to this gap at the end. Okay, so you have to subtract that at the end. Then you will get the protein ligand interaction energy using the quantum mechanics. So even you can use even MPT level of theory or MO6-2x level of theory to calculate the protein ligand interaction energy. So we have used it for some test cases, where the force field method failed. For example, FTDNP is supposed to be the strongly binding to tau, but then the force field method predicted that they are binding to amyloid beta fibril. But then with the use of QM fragmentation scheme, we were able to reproduce that the FTDNP is a better tau tracer than the amyloid tracer. Okay, so we have methods, which can predict the binding affinity in a better way than the force field method. What I think is like it's a little bit competition demanding, but then we can contribute to the improvement in approach. That's not a problem. But then, as I said, the quantum mechanics is very time consuming. So rather, we have been a little bit working recently on whether we can use machine learning based methods for predicting the druggability property. Okay, because these type of machine learning calculations, you can just do it in a laptop or something, like with minimal resources you can do the calculation. So we have been a little bit testing on this monomeric SSD. So we try to develop some machine learning model. Before that, we want to test how well the force field methods are performing in predicting the experimental binding affinity. So we had like 3,700 comments from MEBL database, which are known to having activity against this target. So we had the chemical structure, we had the IC50 values, and then we did molecular docking using Autodock Vina, then MMGBSA, and we found that these methods are not able to reproduce the experimental binding affinity in right way. So we used machine learning methods where you compute all various descriptors. We computed about 1054 descriptors using Paddle software. Then along with the IC50, we have developed various machine learning model. We found that KNN model is the outperforming, best performing one. Then when compared to remaining machine learning models, and it was able to reproduce the experimental binding affinity in the best way. So the idea is that we can use the machine learning approaches to predict the drug-like properties. Okay, but this approach, you see that here we only focus on single target, right? But then let us say you have multiple targets and you want to predict the binding affinity, then you need to go for like structure-based machine learning approach. Okay, so we also try to test whether how good are the QM-based and machine learning-based methods in predicting the binding affinity. So we have tried the onion net, which is a neural network, to predict the binding affinity. It uses basically the protein ligand interactions as features, then it can predict the binding affinity. It is basically a regression model where you can predict the binding affinity. So we can see that of course the machine learning methods are outperforming when compared to QM fragmentation scheme, because not only they produce a trend nicely, in addition to that they also reproduce the trend quantitatively. But if you see the QM fragmentation scheme, so here I show you two of the methods. One includes solvation energy, and that means it accounts for the acoustic environment, for the proteins, and the other one doesn't. So the red dots belong to the QM fragmentation method, including the solvation energy term, and not the black one doesn't have the solvation. You can see that if you don't include the solvation, then method is not performing well. See, even though the quantitatively the method QM fragmentation scheme is not doing well, but then qualitatively still reasonable. Okay, so you can really, when compared to let us say force field methods, still you can rely on this method, okay, to predict the druggability. Same, we also tested the solvation energy, because if you can compute solvation energy, then you can calculate permeability and other properties. So here it was like graph theory based methods where you describe the ligands and the proteins as graphs, and so nodes will be like atoms, and then the connectivities will be edges. So then you can build the interaction between them. Interaction is then you can predict the solvation free energy. So there also we found that machine learning methods are really doing so well. Then comes the quantum mechanical PCM method. Then comes the fragmentation schemes, where you describe the sums explicitly. Okay, so the idea is that machine learning methods are outperforming even the quantum mechanics based methods. So I think that was the thing for the druggability prediction. Then we also did a lot of modeling to study the diagnostic agents when they bind to various fibrils, what happens to their structure, optical properties, and their conformational dynamics. So all these things we were able to do. But then thing is that since I don't want to run away from the schedule, I will quickly wind up saying that just one example. So we have been working in collaboration with Govindaraju, who is from JNCA, sir. So he had developed many compounds which are suitable for imaging or therapeutic purpose of Alzheimer's disease. So in this particular paper, he scanned various compounds, TGR 60 to 65. Then through modeling, and we found that the TGR 63 is one of the compound with the highest binding potential, and then also it is able to disrupt the fibrils to in a better way. So we could show that the TGR 63 compound is able to disrupt the intermolecular hydrogen bonds and solve bridges in amyloid fibril. So that way they can disintegrate the formed fibrils in the brain. In that way, then if we can achieve that, then our body machineries will take care, and then they will remove these soluble fibril fragments. So Govindaraj also verified this in mouse models, and then the interesting news is that this compound now is taken forward by some pharma company in Delhi, and then they wanted to carry out the clinical trials for this compound. Okay, so in fact, my contribution in this project is that I was doing the computational modeling, and I was showing that which are the binding site, and then what is the reason for the amyloid busting property of these compounds. So I'm very happy that there is some compound coming from India, and which may end up like a potential therapeutic compound for Alzheimer's disease, where we don't have any therapeutic compounds so far. So it is really a good news. Like we can use computational methods to understand the binding profile of various amyloid tracers or tau tracers. We can model the binding affinity. We can use different approaches, ranging from force field to quantum mechanics to machine learning based methods, and you can really improve upon the binding affinity prediction or druggability prediction. So there is a lot of scope to use the computational methods to develop diagnostics and therapeutics. Only thing is we should know what is the right approach and what type of systems are which one we want to use, and we should know what is the limitation of different methods. So we can blindly take any results. Sometimes you need to analyze, like the results we have got, is it making sense, or or so we always need to check what is the error associated with the results we have got. So we cannot just take the numbers in a blind way. You will have to give understanding. You will have to explain why we are getting such results. I think so that's a way to use the competition approaches. Many times you may not get quantitative results, and it doesn't matter. Let us have you have like billion compounds and you find like top 100 compounds. Then you can take them for the experimental screening, clinical validation. So that is already a big achievement, right? Because you have cut down all these billion compounds and you only have 100 compounds. You have narrowed down the search space or chemical space, which is like now easily you can handle them using computational experimental approaches. So that way, the computational approaches can be used in a complementary way, or even in a in a leading way. Then the experimental approaches can follow them. So it's like you can put them in a different way, and then you can get maximum benefit out of the computational modeling. So that's it I want to say here. And if you have any questions, you can ask me. Otherwise, yeah, I thank you again very much, the organizers, for giving me this opportunity. At least hope in future I can come and give you a presentation offline. I'm looking forward for that. Thank you very much.
Thank you very much, sir. Now, if any of our audience want to ask some question, can raise their hand. Okay, if not, then let us thank Professor Arul Murugan, sir, for delivering a wonderful talk here in our seminar on the behalf of MLT College and the organizing committee.
Thank you very much, organizer. Have a nice day. Best wishes to you. Yeah, best wishes to you. Okay, bye bye. Thank you.
Now we will move to next program, the oral presentation session, and for that I will ask my colleague to come here and proceed the session.
Thank you, sir. Thank you very much. And for the oral presentation, we have the chairperson, Dr. Sikha Chaudhary, madam. So I would like to request her to come over the dais so that we can proceed for our oral presentation for the research scholars. Sikha, madam. Madam, आप अभी chairperson. आप इनको लेके जाइए. As listed, OP01, Ruchi Jain, Department of Chemistry, SBSS College, Begusara. Are you there? Ruchi Jain. Next is Akriti Madhu, Department of Physics, BNMU, Darbhanga. अच्छा, आकृति मधु आप ठीक।
वीडियो बना दीजिएगा। Good afternoon, everyone. I am Akriti Madhu, research scholar from LNMU Darbhanga. My guide's name is Dr. UK Das from CS.
इस माइक को यूज नहीं करना, इसमें माइक है ना, उसे से यूज करना, ठीक है।
ये कैसे बोला? From CM Science College, Darbhanga. My topic's name is Soliton propagation. Here I give some explanation about this topic. The content is introduction, solitons in optical fiber, advantage and disadvantage of solitons, results and discussion, conclusions and references. Introduction. The solitons are a light process that do not change during propagation. Eco हो रहा
Next presenter is Meena Kumari Ray. Then OP04 Babita Kumari. Number 5 Kirti Vardhan Gautam. I think they are neither online nor offline. So next is Abhishek Kumar. Number 6 Abhishek Kumar. So next Badrinath Jha, Neetu Kumari, Praveen Kumar. I think Praveen Kumar is online.
Yes, sir.
Okay. Then you can give your presentation.
Yes, sir.
So try to be very precise, complete within 5 minutes. Thank
Okay,
you.
sir. Okay, sir. Please give me permission for slide share. Good afternoon, everyone. Good afternoon, everyone. Myself, Praveen Kumar, research scholar, Patna University. Under the supervision of Dr. Vinod Prasad, Department of Botany, Bihar National College, Patna University, Patna. Now I'm going to discuss about my research article, the study of effect of dimethiate 30% EC, a pesticides on cytogenotoxicity of Allium sapa. My research article again, the study of effect of dimethiate 30% EC, a pesticides on cytogenotoxicity of Allium cepa. The genotoxicity potential of dimethiates, a pesticides has found widely used in onion crop field presently. A study aimed to evaluate genotoxic effects of various concentrations of these pesticides. Treatment of rooted bulb with different concentration, 0.2%, 0.4%, 6%, 0.6% of pesticides and mitotic index were assessed at the time of interval of 24 hours, 48 hours, and 72 hours. The result indicated that dimethiate significantly increased the genetic abnormality in different concentration and treatment period when compared with control plants. Meiotic analysis were also made from the treated as well as control plant. The data obtained this study shows that chromosomal aberration assay can be used to detect threshold dose or possible genotoxicity of pesticides in Allium cepa. Pesticide. What is the pesticides? Pesticides are substance or mixture of substances which is designed for crop protections from pests, weeds, and plant disease. Their application is significantly increase the productions and productivity of commodity to feed the ever-growing population. A total about 292 pesticides registered in India, and it is estimated that there are around 104 pesticides that are continued to produced or used in India. There are so many pesticides are frequently used in agriculture area, progressively increase in contamination in environment. As a result, physical and biological degradation product of air, water, and food. Prolonged exposure of these contaminants enters into the food chain, causing genotoxicity of gene pool. Studies have proved that pesticides have been tested with wide range of mutagenicity, such as gene mutation, chromosomal aberration, and DNA damage. These are occurred because of either a DNA replication or synthesis of nucleoprotein complex, which results in breakage of chromosome and abnormal segregation. Cytogenetic factor such as mitotic index and chromosomal aberration in root tip cells of allium cepa are the parameter used to determine the cytotoxicity. Mitotic index is accepted as a criteria for determining cytotoxicity for all living organisms. The cytotoxic level can be determined by change in mitotic index ratio. The cytotoxic substances shows their effect on mitosis by inhibiting microtubules formation. Methodology: young and fresh onion bulbs of uniform size were used. It is cleaned and washed with double distilled water to remove the unwanted substances adhered to it. The older and primary roots were removed and the bulbs are placed directly on a specimen tube containing tap water. After 24 to 36 hours, roots from the bulb started to emerge. Once rootlet has grown 2 to 3 centimeters, are treated with different concentration of pesticides for varying hours. After completing the treatment, the root tips were harvested.
Praveen?
Yes, sir.
I request you to conclude your slides.
Oh, okay. Mitotic index, number of dividing cells by total number of cells into 100. That is the mitotic index calculated from this formula, and the percentage of aberrant cells provided in slides. Next slide. Different types of chromosome abnormality were seen in the root mitosis of allium cepa. That is the stickiness, dissolution of chromosome, a sticky metaphase, C metaphase, a sticky anaphase showing multiple breeds, anaphase with ring chromosome.
Praveen, your time is over. You can conclude it.
Okay, sir. But a figure showing the figure legends. That is the sticky anaphase with chromosome anaphase laggards. Different types of figures were taken in the microscopic techniques. That is the giant cell, a sticky chromosome, and the next the binucleated nuclear lesion, and different types of chromosome abnormality were seen in the root tips of mitosis. Results that different concentration.
Okay, Praveen, Praveen, are you listening? Your time is over and next participants are waiting. So thank you for your presentation, and we will move for next presenter.
Okay, sir. Thank you. Thank you.
Thank you, sir. Next presenter is OP11, Dr. Rajkumar Sardar.
Praveen, you can remove the slideshow.
Okay, sir. Okay.
Our next presenter is Sumit Kumar. Sumit.
So can I start? Hello. So good afternoon, everyone. Today I am going to present my research work done on the topic fissile synthesis of carbon nanotubes, nanochains, and carbon quantum dots using charcoal powder, and exploring its structural, morphological, optical, and thermal properties. So for this presentation,
Sumit, your PowerPoint is not visible.
Oh, now, sir, is it visible?
Yes,
Yes,
okay
it's
now.
visible now.
Okay. I am Dr. Sumit Kumar from KK University in Nalanda, Bihar. So today I am going to present my research work done on the topic fissile synthesis of carbon nanotubes, nanochains, and quantum dots using charcoal powder, and exploring its structural, morphological, optical, and thermal properties. So for this presentation, I have included synthesis characterizations and properties of this work mainly. So the carbon nanotubes, carbon nanochains, and carbon quantum dots were synthesized from charcoal powder. So it is very easy. You can find everywhere charcoal. Using this H2SO4 and HNO3 combination mixture of these two by changing the pH using NaOH and dried to at 60 degrees centigrade. And after getting these three carbon nanostructures, the yield of the synthesized carbon nanotubes and carbon nanochains was found to be half of the mass of the precursor, means charcoal powder, whereas the yield of carbon quantum dots was found to be 1/3 of the mass of the precursor. Means the yield of the carbon quantum dots was less than carbon nanotubes and carbon nanochains. So this is the schematic diagram of the synthesis procedure. And for next sliding, we have mention some notation for the samples. For charcoal powder, we have done C note, CNTs, C1 for CNCs, C2 and carbon quantum dots C3. So for structural properties, we have used Raman spectroscopy, and it is very powerful tool to find out the structure of any graphitic materials. So for C note, C1, C2 and C3 means carbon charcoal powder, carbon nanotube, carbon nanochains, and for carbon quantum dots, we got in all these Raman spectra D and G peaks. So this confirms the formation of graphitic means form of graphitic nature. And after that, we have calculated ID upon IG value of all these materials, and sp2 crystallized size of sp2 domains also, because sp2 domains is very important for graphitic materials. So these Raman spectroscopy results confirm the formation of graphitic carbon nanostructure. After that, what is this?
Yeah, Sumit, you can conclude now. We are running out of time.
So this transmission electron microscopy shows that clearly shows the carbon nanotubes, carbon nanochains, and carbon quantum dots, the formation of these three. After that, we have calculated, we have observed optical properties and thermal properties also, but due to the shortage of time, I am not explaining these things. So conclusion of this work is the present work was focused to explore the charcoal as one of the cheapest carbon source for making different types of carbon nanostructures.
Sumit, your voice is not clear. So I think you have finished now.
Developed critical conclusion. So this analysis also shows that the chemical treatment of on the charcoal powder, the stability of materials
Sumit,
changes.
please remove your slide.
Okay, sir. Thank you very much.
Our next speaker is Dr. Sujata Chaudhary, Department of Physics, Harvard University, USA. On behalf of the Department of Physics, I welcome Mrs. Sujata Chaudhary.
Can you hear me? Good afternoon. Can you hear me? Hello? Hello, can you hear me? Okay.
Yes, you are audible, sir.
Okay. Hold on. Is it able? Are you able to see my PowerPoint?
Yeah, visible, sir. Visible.
Okay. Good afternoon, and I would like to thank you to everyone before. Sorry, my date is wrong here. It is. I'm sorry, May 23rd. Good afternoon, everyone. Thank you for giving me the opportunity to present my talk. Actually, this work is also under review, but I would like to give it a little bit details about my recent work on topological magnetic topological insulator. So the title of talk, the effect of external magnetic field and chemical substitution and quantum phase transition of antiferromagnetic system. But here I would like to discuss a little bit more about how the other effect is playing the role. This work is actually done in collaboration with my collaborators, Kevin Garrity and Francesca Tavaza, and there is some external experimental collaborator from Brookhaven National Laboratory. So first, I would like to means thanks to my collaborator, NIST, Francesca Tavaza as mentioned, and Kevin Garrity, and from TIFR, Bahadur Singh. And from Northwestern University, Arun Bansal, Barun Ghosh, Bao Kai Wang, and Matthew Madzel. So experimental for the Raman data, I would like to thank Angela Hyde-Walker. Experimental for synthesis, the grow the material, actually it is Sean O from Rutgers University, and X-ray is Slack Josh Turner. And here also I would like to thank to my student, Gadir, Alana, and Jalen and Shogoto. So first question is that why the quantum material is most important? Why we look at the quantum material? So until now, we notice that there are several development with the nanoelectronics, and we first want to know what is quantum material. The quantum material, if I would like to say in one sentence, we can say that the quantum material are not new, but their property was discovered, which was not discovered before graphene very quietly. So that is, they are giving some exotic and unique and often incredible property. So they could be like quantum entanglement, quantum fluctuation, quantum coherence, quantum liquid phase, and so many other stuff. So recently, 2016 and 2012, if you notice that I have taken from the editorial from the different journal, from like Nature Physics and Physics Today, they are saying that all these emergent phenomena common in condensed matter, but the study went beyond the strongly correlated system. So when we are looking at the quantum material, that is really, really very important for us to understand what is going on if we would like to understand the physics and if we would like to go to the quantum computer regime. So next thing is like that. And here also I would like to say that if you lay the quantum material, all those properties need our magnetic system. So why it is important? Look at that. I have taken from, it is from Wiki Commons Intel. So when it started the semiconductor, we use the vacuum tube, then transistor, then integrated circuit, then we are using Intel Standard Bridge and very, very small. But if we would like to, and if you notice that the speed of the computer is coming very slow down and it is smoothing down. If we would like to use faster communication and store more data, we have to go to the quantum regime. And it could be possible to using one atom. The question is that, is there any option? Yes, there is an option. There is one option is Google quantum computers. There is a Microsoft quantum computer and IBM quantum computer. I am working with the IBM quantum computer to develop this quantum computer faster, and we can use that in future communication. All this quantum computer are in initial stage. There is a lot of noise. There is a lot of things we cannot do that, but we are developing different kind of algorithm. The question is where I am working. I'm working in that if you notice that how the quantum computer and classical computer is interface and they are communicating. My first focus is that topological qubit. And also this topological qubit, we need different kind of superconductor, magnetic system, non-magnetic system, whatever, but it should increase our communication, speed up, and storage data. So here, how this quantum material journey started. First, you have to understand what is the topological insulator. If you look at the first figure, what is the ordinary insulator? Ordinary insulator, there is a conduction band and valence band, and there is a band gap. But in the cases of what is the example? Gallium arsenide, any kind of solid argon, but when there is a special topic like little bit stronger spin orbit coupling, like heavier material, they have a conduction band. That means they are inside, they are insulator, but the surface is they are continuously conducting the electron. Means top bottom and the lower bottom will give you different kind of direction of the electron transportation. And what is the example? This is the one first example, it's experimental observed in that case. So I am fortunate, one of the father of the topological insulator, Charlie Kane, I work with him. So one day I asked, what is possible using the topological insulator? He said, we don't know what we can do, and we have to wait another 10 years to understand what we can do. In 2015, he made a famous comment. I am reading that comment. This noble electronic state of matter is gapped in the bulk and support the transport of spin and charge in gapless edge state that propagate at the sample boundary. The edge state, insensitive to disorder because their directionality is correlated with the spin. So that means if we can use this property, it is possible uninterrupted transportation of electron. And in this case, this is actually look the topological insulator. What is red is saying that conducting surface and blue is giving insulating bulk. So top is the up direction. This is the clockwise direction it is rotating, and it is on the other side, it is opposite direction it is going. This is actually the topological insulator it is saying. So top and bottom, they are direction is completely different. So what is the first? When I started working in 2010, at that time, there are 3 different kind of topological insulator came, non-magnetic. All this theoretical prediction, and this is another prediction simultaneous for bismuth, and they showed how the spin orbit coupling is making effect. Next thing is realization, experimental from Stanford University first developed this one, and second it is Princeton University. They also measure experimentally that could be possible for any kind of bismuth solenoid and bismuth telluride structure. The question is that, okay, we got the topological insulator. What is the next step? If we would like to get some kind of quantum anomalous regime and quantum material or any kind of system, that should be give us some external magnetic field we require. So what happened if we don't use the external magnetic field? We need some magnetic, which is the intrinsic property. Let's start with that. And that started investigation for the magnetic topological insulator. Here, I would like to use my very small means collected result from the recent development and the family of MBS. So the question is that what is the MBS? MBS is the one of the most important part. This is septuple layer. If you look at this structure, we can see there is 7 layers. In the middle layer, it is a magnetic system. It could be manganese, it could be iron, it could be cobalt, it could be vanadium. But in this case, manganese has, because their valence band interaction. So if you notice that it is an inversion symmetry completely, it is in the middle. If you will consider this is a mirror, we will get selenium, bismuth, selenium. So it is completely. First, we tried to synthesize that one. My collaborator was trying to dope the bismuth solenoid structure by using the manganese, but they found septuple layer. And when we focus on that, how it is working and how it proceeds, we will discuss. This part of the talk, I will focus particularly different chemicals and their doping process. So already I discussed this one. Second thing is that what will happen if I will use the magnetic system? There is possible quantum Hall effect. What is the quantum Hall effect? The edge mode propagate in a single direction and so no possibility of scattering if the bulk is sufficiently wide and insulating. And that is the one of the important thing if I will use the magnetic. So that means quantum anomalous, quantum Hall and quantum anomalous Hall effect we will get. And there is another possibility we can get the quantum spin effect. Edge mode propagate in both direction. Scattering is possible with flipped spin. So that means using the magnetic system, we can control their direction, we can control their property, we can using different way, you can tuning their property. What is the requirement for that one? Let us consider 2D system. It must be the magnetic. So the anomalous Hall effect at any, we don't need any kind of external magnetic field. There is a dissipationless, that means it cannot stop. Must be insulating, only the edge state is possible. And also quantization of the system. So here we can see that this is the requirement. And also quantum anomalous Hall effect, when we put the state requirement for the material, what kind of material do we need? Mostly ferromagnetic material or metallic. Magnetic order is difficult to realize. Magnetism and topology may be against each other because magnetism always break different kind of property and disruption. So we need this kind of, to overcome this, we need some kind of material. So this is the one famous example. Again, I'm using bismuth solenoid. What will happen? We will use the bismuth solenoid and doped by the manganese or chromium. So what will happen? This is the one of the first Hassan group from the Princeton they did, and they found out there is band gap opening. So we are in the quantum anomalous Hall effect region. And when they're using the chromium, there is a band gap. So that means from the metallic system, we are going to a semiconductor situation. The question is that all those experiments done in sub-Kelvin, that means it is less than 1 Kelvin. So question is that is not possible. We need the liquid helium, and if we can achieve that one, it is be very costly. If we would like to use for the human, everyone use, we need some kind of material which can operate higher temperature, at least nitrogen, liquid nitrogen region. So that's why our focus is that higher temperature magnetic topological phases, larger band gap, and robust single crystal. As I mentioned, in this case, a lot of people are asking us the MBS, but because MBT is easily synthesized, so people were graviated to MBT. So here I'm changing my nomenclature and saying that it is MBT system. Let us what is going on in the MBS first. Okay, so if you will look at the periodic table, different material, we tried all those material. But in the cases is when we notice what is the structure, we are setting R3M symmetry, which is giving us the topological. But the ground state is MBS, it is giving is the trivial insulator. In that cases, to synthesize MBS using this kind of septuple layer, we need MBE growth. And our collaborator from NIST, they did. And after that, actually started the working on MBT. People started working on MBT. I still remember 2018 when I presented my first talk on MBS, there are only 3 people presented on the same topic. In 2019 and 2020, it was a 200 paper submitted at APS conference to present that work. So that means it is exploded about this system investigation. What is the difference between bismuth solenoid and bismuth MBS? This is the septuple, quintuple layer, and this is our septuple layer. So all those things is giving us their symmetry is same, but the number of atomic layer are different. In this case, first we started, don't need to put any kind of manganese system, we put palladium, lead, and we found out it is similar to as bismuth solenoid. This is the given us, this is a strong Ti material. What will happen if I would like to use manganese in place of that? There is two phases, antiferromagnetic and ferromagnetic phases. Antiferromagnetic phase is an axion insulator, is a semiconductor, but when we are giving us the ferromagnetic, that means we are applying some way the magnetic external magnetic field, we are getting wild semimetallic phase. So that is the wild semimetallic. Again, ground state is antiferromagnetic, which is an axial insulator. And there is a band inversion. If you notice the color code, there is a band inversion, it is happening. And when band inversion is happening, that means that is opening the band gap in presence of the magnetic field. Next, if we are applying the external magnetic field, is it depend on the direction? Let's see what happened. When we are applying the two different direction magnetic field, it is behaving, the band structure is behaving to different way. If it is Z direction, it is the point, but nodal line we are getting when we are applying the x-axis. So that means we can control our structure or electronic property using actually the direction of the magnetic field. So while node and while nodal line, this is the very robust topological property, but they depend on the external magnetic field. Another feature, when it is wild semi-metal, we need the Fermi arc, and we find out this is the Fermi arc. They are in opposite direction, left arm arc and right arm arc. And similarly, when we published our paper in archive, lot of other papers started to come and they got the similar result. So that means it is possible, that is the theoretical prediction is working. So what is the experimental? It is possible. And is it quantum Hall region? So we took surface along 0, 0, 1 surface direction. What is the TRS? TRS time reversal symmetry. When we notice that it is a 32 even layer, Chern number is 0, but odd layer, it is giving a Chern number is 1. So that means, again, the depend on the layer number. So if we will control the thickness, we can get to different kind of property, Chern number 0 and Chern number 1. And depend on the Chern number 1, it is quantum anomalous Hall region, it will predict. What is the Chern number 1? Chern number 1, it is saying confirming quantum anomalous Hall effect. Chern number 0 is saying no. There is, so that means even and odd is playing the role. That means thickness is playing the role for the topological property or the quantum anomalous Hall effect of the MBS. Okay, we check the thickness and we found out this is the band gap, and the band gap is reducing. What happened? In that same cases, it is happening for the antiferromagnetic cases. If you notice, band inversion started when there is certain number of layers. That means we need stronger magnetic field and means stronger presence of the magnetic atom and the thickness and the spin orbit coupling for layer. And we found out also the 8th state of the system. So it is proving us that, okay, if we are using the different kind of thickness, we can control their property. From there, we concluded ground state is AFM, antiferromagnetic. When it is ferromagnetic, wild semi-metal, and when the direction is changing, it is wild node. And when it is more than 7 or equal to 7, it is a Chern insulator. And when it is ferromagnetic system, means when it is greater than 3, it is a Chern insulator. So it is giving us the confidence that that material could be explained. And what is the phase transition temperature magnetic? It is 50 Kelvin. Actually predicted, we predicted it is 70 Kelvin by the theoretical. There is some numerical error. Experimentally, they found out it is 50, around the 50 Kelvin. Okay. Second thing is we are going to the domain wall region. So what is saying that when we are doing the work on MBS, at that time, several paper was coming on the MBT, and there is experimental study was going on. And they found the most important part, some people were getting the quantum anomalous Hall effect, higher magnetic field. Theory is saying odd layer system, zero field. The question is that why we need external magnetic field and why we are not getting properly, or some experimental and theory is not matching in these cases. So what we did, we think that is actually the presence of the magnetic domain. Okay, we got that idea, we try to. So we did DFT calculation and our tight binding model and try to understand if the DFT calculation and tight binding model is working. And we found that it is matching with the tight binding model and the DFT. This is the all DFT result, and this is the all tight binding model result. And it is giving us that confident our theory and our Hamiltonian is more accurate. So what we did, using our tight binding model, we check the temperature dependent model. And we found out experimentally it is saying 25 Kelvin, it is phase transition. And we found out above the 25 Kelvin, there is a no band gap. Band gap is closing and there is a band gap. So it is temperature dependent. And we did the surface gap and the bulk gap. And we noticed the surface bulk gap is always constant. It is not changing with the temperature, but the surface gap below the some temperature or above the some temperature surface gap, it is closing down. And whatever about the Chern number, we found out the Chern number. If you notice that after certain temperature, Chern number is changing, it is 1, and after the temperature is decreasing, Chern number is changing. So we concluded that what is happening? Bulk band gap is not closing, surface band gap is closing. So there is two different things we are finding. And this is non-trivial TRS invariant we are finding. It is giving us the confidence that, okay, that is theory, DFT and tight binding model, Hamiltonian is right. But the question is that why there is a discrepancy between theory and experiment. So what we did, we make using tight binding model, we use one of the most important part is magnetic domain. We divided 24 into 1 into 6 cell. Larger sphere is giving the amplitude. And we found out certainly that in some cases, the topological band gap or surface state, it is depend on completely the magnetic domain. That means when we are using the surface probe to do the RPS measurement, we are going here and there in some particular region, and where it is the magnetic domain is aligned, and that time we are getting that topological property which is matching with our theoretical prediction. But sometimes it is some other domain which is not aligned properly. At that cases we are not getting topological phases or matching with not DFT result. So summary, that critical bulk gap closer at critical value, magnetic surface closer above transition temperature, and it is also the measure the domain structure. The future experiment we are working on the domain structure, how big is the domain structure, STM measurement, local probe band structure and the temperature, band structure, temperature and magnetic field. We are trying to understand that part with our experimental collaborator. Next things I would like to present about, okay, MBT and MBS have done. What happened if we will consider different chemical system? In place of bismuth, antimony, what is happening? So we did this one, and every cases we get the similar result, antiferromagnetic phase. antiferromagnetic phase, and we try to find out what is the energy difference. We found out that energy difference is reasonable and that is matching with our experimental result. What about the topological phase? Here I would like to give that what topological phase. One of the most important part that AFM phase, all are axion insulator except one part, trivial MSS. That means if I will go, that is that this structure is only the is not a topological insulator. It is a trivial insulator. Okay, let's see how it is happening if we change the magnetic field direction. So we consider three different directions. One is flop, that means out in plane antiferromagnetic to in plane out of plane ferromagnetism, out of plane antiferromagnetism to in plane ferromagnetism, and out of plane ferromagnetism to in plane ferromagnetism. In the MBS case, we found out they are giving two different kind of band structure. Let's see what is happening. So we change, and when we change for the MBS, we already know this is a topological insulator. It will be wild node and wild nodal line. MBT throughout the axion. That is not surprising, but surprising is that if you notice that one MS antimony system, it is a trivial insulator. But when we are going to the ferromagnetic phase, it is giving us wild semimetallic phase. So that means if we can use properly, apply the external magnetic field, we can change the trivial to non-trivial transition, which is most probably most important part. So that means using the magnetic field direction, we can control their topological, that means trivial to non-trivial. So that means switch on and off way, we can change their property. On the other hand, MST is the axion insulator, and all these two, MBS and MSS, both are type 1 wild semimetal. But here, if you notice, their band structure is completely different. There is two different positions, the Fermi energy they are crossing. And when they are crossing, in these cases, we notice that means it is type 2 wild semimetal. So we got that result. Next, what happened? The band inversion cases. We found out the band inversion, and it is depend on completely chemical structure. Their symmetry is different. How they are doing all those usually is giving us the different kind of symmetry. So that means their property is completely depend on chemical composition. Let's start. What will happen when it is Z to X direction? And we found out similar way, it is the robust, it is from point to nodal line direction, but the MST and MBT, so that means it is different kind of topological. So that means selenium and telluride is giving us completely two different kind of chemical topological phase. Okay, so now it is out of plane to in plane direction. Similar way you can find out the topological property is completely, their band structure is completely different. One of the most important part, MST was type 2 topology wild semimetal, but it is now axion insulator. So that means we can control not only accept MBT is robust direction, how we are controlling the magnetic field, which direction we are giving the magnetic field, it does not matter. It is always trying to be the same way behaving. Okay, that's what will happen to the spin orbit coupling. It is showing the strength, that how much it is the spin orbit coupling, how much is the chemical composition, how much is the chemical structure, electron is there, how big is their atomic radii. Their property is also depend on that mixing. So that means if we can dope bismuth with other system, similar kind of property in the periodic table, we can control the trivial and non-trivial property of the material. That's the So in that way, so that means again, okay, we got that the chemical system is that MBT, MBS, MST, both are different to each other. What happened? Take MBT, put into the antimony system. So if you notice that one, this is the means we are trying to system slowly doping the system. In antiferromagnetic case, we are trying, and we found out that their property is ferromagnetic and antiferromagnetic phase. They are different way they are behaving. What is happening to the surface state? This is the case of the surface state. This is the surface state antiferromagnetic. This is the antimony. This is the bismuth. Their surface state is completely different. And here they are ferromagnetic is also different way they are behaving in this case. So that means their chemical things is playing the role. But what is happening when we doing the N-type doping and P-type doping? If you notice that here, N-type doping and P-type doping, N-type doping antiferromagnetic case for the bismuth and the case of the antimony, completely different surface state. And their Char number is giving us the confidence, okay, this could be, and this is the metallic system. So Char number does not matter. So surface state is controllable. Here, P-type doping. When we are putting the P-type doping, antiferromagnetic phase is different. There is gap. Different. And if you notice that it is how close to the Fermi level, but it is going to the means conduction band direction. So there is a shifting, and this is completely depend. Look at that. This is the bismuth and this is the antimony. So chemical doping is controlling their property. Again, in this case, similar way, if we can do that one, controlling in the different position, different where we are putting this doping system. Antimony is far closer to the manganese, or manganese is going away from far away. So that means long range interaction is playing the role in these cases. And we found, and from that, chemical substitution is the topological property we can conclude. And there is the external magnetic field, we can spin orbit coupling, and doping, tuning the topological property. From there, I would like to thank you for the experimental collaborator, and again, theoretical collaborator from NIST and BNL. And thank you for the computational support from NIST, Brookhaven National Laboratory, and EXIT. And thank you for your attention. If you have any question, you can ask me. Can you hear me? Hello,
yeah, thank you very much. Thank you very much, sir, for your wonderful lecture. And now it's open if our audience has any queries. And if not, then let me thank you, Professor Sugata Chaudhary. And on the behalf of MLT College and organizing committee, I thank a lot Professor Sugata Chaudhary for a wonderful talk. And with this talk, the final program of today's session, we have finished. With the permission of our chairperson, I declare the completion of today's session. So we will start tomorrow at 11 a.m. now. Thank you very much for all participants for patience hearing. Thank you.
Thank you.